think we can get started. Welcome everyone to our workshop called ViLMa on visual localization and mapping. First of all, maybe also for the people online, if you cannot hear me, I think you should be able to hear me. Please write it to the chat, and then we see that we fix it. To start with, I want to welcome everyone from our organizers who supported us to set up the workshop, and without them, we wouldn't have been able to set up the event. So therefore, also thanks for all the organizers, for Daniel Krimmers from the Technical University of Munich, from Dima Dahmen, from the University of Bristol, from Lukas Köstler and Stefan Leutenegger, also from the Technical University of Munich, from Raquel Urtasun from University of Toronto, and from Patrick Wenzel, who is here with me from Helsing, and myself, Niklas Seller. For information regarding the workshop, please feel free to visit our workshop web page. Probably you found it already. Also, if after the workshop, if you want to get in contact with us, if you want to ask some questions, feel free. There are all our contact informations, and feel free to contact us if you have questions, if you want to get into discussion. Also, maybe if you have questions to the speakers which we have today, feel free to reach out to us. Before we start with the workshop today, I want to very briefly tell about the history of our workshop series, which we actually started already in 2020. We wanted to organize the first workshop at that time on map-based localization for autonomous driving. And as all of you know, due to the pandemic, it turned out, or it resulted that we didn't had an in-person conference, which was planned in Glasgow back then, but we had an online event, which in the end worked out well. 1 year later, we also had an online event at ICCV, and then in 2022, we had the first time the chance to organize our workshop in person in Tel Aviv at ECCV. However, back then, we still had it the way that most of the speakers were not able to attend, and so we had basically an in-person event, and we had online speakers. And so therefore, for today, we are quite proud that today is the first workshop which we are organizing, which is full in-person. So we made sure that we have all the speakers here, that we only have in-person presentation. And I hope that this, in the end, will help also to have a more fruitful discussion, and also see the faces and get in contact with the people. Furthermore, we decided to broaden the topic of the workshop a bit. Before, we always had a workshop on localization and mapping for autonomous driving, but of course, there are many other applications like robotics, like virtual reality, like augmented reality, where we need mapping and localization. And therefore, we decided to broaden the topic. And I think this is also what you're going to see with our speakers, that we have speakers who are focusing on all different applications, all related to the topics of localization and mapping. In total, we're going to have today for the whole day, so we have a whole day event. We have in total 7 keynote speakers, 3 in the morning, and then 4 in the afternoon after the lunch break. In the morning, we're going to start with Vincent Lepetit from ENPC Paris Tech. Afterwards, we're going to have Lukas von Sturmberg from Valve Corporation. We're going to have Jakob Engel from Meta Reality Labs. And then after our lunch break, we're going to have Peter Conscheder, also from Meta Reality Labs. We're going to have Laura Letache from NVIDIA. We're going to have Sebastian Scherer from Carnegie Mellon University. And last but not least, we're going to have Mark Polyface from ETH Zurich. And also one thing which we planned for this workshop is that at the end of the workshop, we're going to have a panel discussion with most of our speakers. So it's also some new format which we wanted to try out, and which we also hope that it helps to encourage discussion, to encourage the exchange with all our speakers. So then let's briefly look over the schedule. So we are currently in our introduction, and as I said already before, we're going to have the talk by Vincent Lepetit, who is already here. Afterwards, the talk by Lukas von Sturmberg. Then we're going to have a 30 minutes coffee break. and then afterwards the talk by Jakob Engel. For all the talks, we have about 30 to 35 minutes, and then we have like a 10 minutes Q&A session where all of you can ask questions and yeah, to have a bit of a discussion. Then in the afternoon session, we're going to start with Peter Concheater and with Laura Letaché. Then we have a coffee break again, and then Sebastian Scherer and Mark Polyface. And after those two, we immediately going to have our panel discussion, which we now have for 45 minutes. I think, yeah, we're going to see how fruitful the discussion will be. And after that, we're gonna leave you in the evening, and hope that you afterwards have a nice conference here in Seattle. So therefore, we really hope that you will enjoy the workshop, and I think we immediately start with our first speaker. So yeah, maybe we do it like this, that you can set up, and then I introduce you in the meanwhile. This one on page in my hand. Okay. I would say some words. Okay. The mic is working as well. Can you hear? Okay. All right. Yeah, so we are happy to have Vincent Lepetit with us, who is a professor at ENPC Paris Tech. Before that, he was a professor at the Institute for Computer Graphics and Vision at Graz University of Technology. And before that, he was a senior researcher at EPFL. Currently, his research is focusing on 3D scene understanding, and especially he's looking into reducing the supervision needed for 3D object and 3D environment reconstruction and modeling. And probably all of us know Vincent or know the work of him about Brief, the feature descriptor, for which he and his colleagues in 2020 received the Conderic Test of Time Award. We are quite happy to have you here, Vincent, and the stage is yours.
Thank you for the introduction. Thank you for the invitation. Yeah, so I work a lot on localization, camera localization, and so there's many works these days about localization. So then I decided that it was probably time to do something a little bit different, and we move relatively recently about active mapping. Yeah, so sorry about the silly title. I was looking for something smarter, but that's anyway. So that's yeah. So today I'm going to talk about active mapping. So let's say that we want to reconstruct a 3D model of this new, of this nice castle. So that's a castle in Germany. So the German speaker can probably help me. I'm sorry. So that's the Neuschwanstein. Oh, okay, thanks a lot. So that's. So I picked this example. Okay, so it looks nice. I picked this example because it's not too difficult, but also not trivial, because you have these fancy towers. If you want to create a 3D model, you probably it's not trivial. So you need to turn around the castle. So let's say that you can take a drone with a camera. You try to move the drone around the tower, so to get something like that. So that's something that could work. except that if it's myself who is going to pilot the drone, or probably any professors in computer vision, you would get something like that. Uh, that's uh, that's that's still very challenging to drive, to pilot the drone, to get a trajectory which is going to capture images, so all the images that you need to create the 3D model, and also to have a trajectory which is not too efficient. So basically, so something that an expert, a human expert, can do that. A computer vision professor probably not. So that's we wanted to work on that, and basically to have an automated process to do the mapping. So to give you an idea of where we are aiming, that's the kind of results that we get. So you can see the trajectory of the camera of the drone rotating or moving around the castle, and then from that we can get a 3D model. So maybe so that's purely in simulation so far. So it's not a real drone. We assume that the controls that we send to the drone can execute them perfectly, so that there is no win or whatever. When we know exactly where the drone is. The trajectory is probably not super optimal because it does a lot of things. Maybe a human expert with a lot of experience in capturing 3D models like that would be more efficient, so would be faster, would have a shorter trajectory. So we are not there yet, but I will try to explain why it's actually a very challenging problem. So actually, so that's not a new problem. So that's if you look back at the history of robotics, so that's a problem that people were already addressing a lot. So it's about making a robot explore a new scene. So that sounds like an interesting problem. It was called next best view search, or the next best view problem, in the sense that you have a robot which is somewhere, has already explored a little bit of the scene, so you already have a little bit of a 3D model, so some starting or a first state of the mapping of your environment. The robot maybe is maybe capturing images, and from that, you would like to have an algorithm which decides where to move next in the next step to capture, to learn as much as possible about the world. So the problem is relatively clear, but that's actually pretty challenging. So you can imagine. So you saw a little bit of this scene. Where should you move exactly to capture these things? So especially because you don't know the rest environment yet, because that's what you are looking for. What would be the optimal trajectory? What would be the algorithm to decide where to move as less as possible, but still learning as much as possible from about the world. And so I will present what we did in the last 2 years, and we'll explain also the limits and what we can do to solve that. So there is one challenge, which is, so we are interested in covering as much as possible the surface. So that's the surface that we see, but it's very difficult to deal with surfaces, and most exactly uncertainties about surfaces, because you need a representation of the surface that would capture the uncertainties, and you want to optimize the uncertainty. So it's getting very, very messy. So what we are going to do is to work with the volume of the scene. So I will explain what I mean by that. But let's say that we can build a function, so that's going to involve deep learning at some point. So this function is going to be represented with a deep architecture. But let's assume that we manage to build a function that I called gain pose, and so this function knows already what we have seen so far, And then given any other pose where we move the camera, it's going to tell us how much new stuff, how much new surface we see from this new pose. Okay, so that's we already moved a little bit the camera, we learned a little bit about the world, and now we try to estimate if, okay, so if I move the camera there, how much new stuff I'm going to see. So that's what I try to represent on my slide. So that let's say that we already saw this face of the castle. So now, if we move the drone over there, we'll see more or less the same thing. So we gain nothing. If we move there, it's much more interesting because we see a new face, a full new face of the castle, and that's definitely something that we want to learn. And then, so starting from that, once we have this function, we can imagine different types of algorithms. So we tried something which is very, very simple, probably greedy, but still relatively efficient. So there are some limitations, but definitely still useful. So what we do something like a gradient descent. So we just so given the position where we are currently, we are going to sample some poses around where we are, and then we just pick the pose that maximize our magic gain pose function. So if it's this one that maximize our prediction of the surface, so the new stuff that we are going to see, that's where we are going to go. So it's definitely not optimal. We can probably imagine something better, so more clever to define the trajectory from this exploiting this gain function, but that works already pretty well, at least on outdoor scenes. And so yeah, that's how we try to explain how we created this function. So as I said, so what we're really interested in is in terms of surface, because that's what we want to reconstruct, but dealing with surfaces, so dealing with the uncertainty with surfaces, it was really, really difficult. It was really, really messy. So we had an intermediate step where we consider the volume, and from the volume, magically, almost magically, we can compute the gain on the surface. So we'll talk first about the volume, and then from the volume we can move to the surface. So let's say that the drone is somewhere there. It looks at a wall. So what can we say about the scene from this wall? So this part, of course, is going to be empty. So between the camera and the wall is going to be empty. If we think purely in terms of geometry, we cannot say anything about what is behind the wall. Okay. But in fact, we can be a little bit more clever and maybe a little bit more accurate about what we can predict. So if we have some prior about the world, when we see a wall, we know that, so just behind the surface of the wall, there is some thickness. So without seeing anything else, we know that behind the wall is going to be full of matter. So that's we know that there is no surface, so that there is some thickness over here. And behind the wall, so we know that the wall is going to end at some point. Then it's probably going to be empty, and then we don't know anything yet. So there is some prior that we can learn about what is not seen so far, just from what the surface that we see. Even if we never saw this part, we still have something to tell about this thing, and we can exploit that to basically create more efficient trajectory. And maybe so far another example. So if you see something like that, a wall which is curved. So for example, the towers of the castle. It's probably going to be like a cylinder, so that it's not you are not sure yet, but it's so this part is probably not empty, and then there is some spectrums behind this curved wall. There is something like the same reasoning for the wall. And if you move a little bit more, so that if you have a full trajectory, if you see three walls with this kind of arrangement, so the inside is probably full, then from the part that you didn't see, there is some gradient, so there's still some uncertainty about this value. So what I want to say is that if you can learn something about the inference from the surfaces that you have seen so far, you can infer some uncertainty or things that are more likely than others about the surface or beyond the surface that you have seen. And so we are trying to exploit this kind of prior knowledge. And so just to say, so it's difficult to represent, but basically our algorithm is going to compute this kind of 3D probabilistic field. So that's what we try to represent there. It's a bit messy, so it's difficult to visualize, to represent, but inside the algorithm there is really this 3D volume, this probabilistic 3D volume that we compute. And so this probabilistic field is going to be represented as a deep network. So that's how we can get this prior. Okay, so for some equations, but without going into too much detail, so basically that's what we would like to compute. So that's this probabilistic field. This F function is going to be represented or computed, built with a deep architecture. And this function, so take a function, a 3D point P in space, basically the camera trajectory, up to the current time, and all the observations which we use the depth maps that are put together to represent the surface that we have seen so far. And so the advantage of this representation is that basically we can probe this probabilistic field by looking at any point P in the volume. That's what we are going to use to compute this surface. The architecture looks like that. I'm not going to detail that, but so that's a modern-like architecture. So that's a modern architecture with attention. Maybe what is also interesting is that we have a way to do some multi-scale representation of the 3D scene that we have seen so far. But okay, so that's what is probably important is that we can probe this probabilistic field just at any point, 3D point P. And then, so that's where the magic happens. So that's when you have a challenging problem. So the best thing that you can do is to have a brilliant PhD student who is going to solve this for you. And so my student found the theorem actually where you can move from a representation in 3D to estimate something in 2D. And so that's exactly what we wanted here. So we have a volumetric representation of the uncertainty about the scene. And by integrating over this scene, over this representation, you can compute something in 2D about the surface of the scene. And so that's what we do here. So that's without going too much into detail. So that mathematically it's an integration, and we simply in the sum over points that are sampled in the field of view of a pose. So that's what you see here. So this function is going to be again a deep architecture. That's a function which is applied to the probabilistic field that we have here. So that's the maths are a little bit maybe involved, but in practice, so that's something which is super useful. We have a representation in 3D which is easy to manage, and from that we get this uncertainty in over the surface. And so at the end, what we get from that is this function, so the gain pose, where we can estimate how much new stuff we see from by estimating this function at any pose in the 3D space. Again, so that's the architecture is a little bit complicated, but so that's it's possible to implement such a function. And so there is one thing that remains, which is how do we learn these F and G functions? So that's just to simplify a little bit, basically what we want what we need to train these two architectures is the surface that we have seen so far and to predict the probabilistic field in 3D. So that's not something which is very easy. So we need to collect data. It's not very clear how we can collect this data. But so we have this self-learning procedure where we let the robot explore an environment, and by matching things that the robots saw before in the past and things that we can estimate after moving a while, we can collect the data, exactly the data that we need. So to explain a little bit more, so to train these two architectures. So let's say that we moved a little bit already the drone, so we have collected already a little some data, so the camera history and observation. So what we would like to train F and G for is to predict this gain function, but for any pose. And so we store what we have seen so far. So that's what is going to be used as input at inference. Then we let the drone explore a little bit the environment. And because we explore a little bit, so we learn something about the volume, about the scene. So we can we store in a memory, so that's a memory replay like other problems in reinforcement learning. So we have this new observation. So that's in terms of a better estimate of the volume of the surface, a better estimate compared to what we had in the past. And now we can pair so this observation in the past and this new observation after a while. And that's exactly the kind of training data that we need to train these architectures. So basically, we store that into a memory replay. So we let the drone fly a little bit, capture data, and after a while, we can use this data to train FNG, and maybe we can rerun again with a better version of FNG to fly again and capture more training data. Okay, so that's the idea, is to capture this experience and match what we have seen at some point with what we can estimate later on for the prediction of these FNG networks. So maybe just one thing. So I just want to be clear. So that's so we use some things for training and some things for testing. So I use the same thing to explain this, but it's really separated. So the data, the 3D models that we use for training these are in the self-supervised way. So that's really not something that we use for testing. So things are done correctly. And just to show a little bit more results, so that's we used some 3D models of some scenes over the world. Here you can see the trajectory of the camera. So again, it's not necessarily completely optimal, but it's not too bad. You could see here basically the view of the drone. So that's what is used by the algorithm to predict the night view. So that's basically the only input. And you can see the reconstruction of the scene so far here, and the estimate of the volumetric occupancy. And maybe I think there is one more example. So this one is in Italy. So to capture the basic. So maybe one the only input to the algorithm is a 3D bounding box, or manual input is a 3D bounding box to make sure that the drone does not fly far away from the scene the scene of interest. So just constrain the poses that we sample to make sure that they stay inside the 3D bounding box. And so maybe to emphasize a little bit the difficulty and the challenge of the problem. So I find it a very super interesting problem. So we try to apply the same algorithm, the same method to an indoor scene, and then suddenly the trajectories are definitely not optimal, and you can see that so it's very natural for a human. So that's an indoor scene with three rooms. If you start here, if you have no experience, even if you don't have any experience, you will probably start scanning this room, then move to the next room and scan this thing and scan the last one. So which is probably the optimal way, the most natural way for a human to do it. With our algorithm, the algorithm is just too greedy. So we start from here, move to the next room because that's where you can see much more stuff, and then move again to the next room to gain as much as possible. But there are a lot of details that were missing in the first room, and then it has to go back in the first room, and then when you do that, you lose a lot of time. It's very difficult to imagine an algorithm which would avoid this sort of things. And so we tried reinforcement learning, so where we predict how we should move. So that's in a little bit more complex environment. So reinforcement, and it works, it does something, but it still gets stuck into a corner of the regularly corners in the room, and that was super difficult to train the reinforcement learning algorithm for this type of things. And I can try to explain a little bit more. So there are many policies that in reinforcement learning that looks good, or that look good, but they are actually not. In the sense that if you move a lot in very far away, I don't know if I want to scan this building, it looks very promising just in terms of gain of surface to move in this the other side of the corner, because suddenly I see much more stuff. But then I forgot to scan the back of the room, and I have to come back. And so that if you have to come back, then suddenly you have a reward which is completely flat, and that's something that reinforcement learning does not like. So at the end, so you have many policies that are locally optimal or locally good, but globally, if you want to scan the full thing, it's super difficult. So we are still working on the problem, just to show you some current results. So that's the current version of the current results that we have with the algorithm that we have been developing so far. So it's definitely better than the standard reinforcement learning, but it's still not completely optimal. I think we can still do better. So it's not perfect. There are things that we still miss. If you're interested to work on this problem, I really find it interesting. So we are working on digital twins. We are starting to work on digital twin. Imagine that you want to build a digital twin of a building, of a factory, or something like that. Suddenly you have complex indoor environments, and it's not clear how to do the scan, or to let a robot do the scanning automatically. And maybe, yes, so that's I want to, if I still have a little bit of time, that's just to mention something which is also hopefully of interest for the workshop. So we have been working on creating 3D meshes from Gaussian splatting. So that's the poster actually made by who is going to be presented by the student who developed most of the things I also presented today. So from the Gaussian splatting to extract a 3D mesh, so we already triangles, and once you have a 3D mesh, you can do whatever you want with the meshes. So you can start animating the mesh. So the students can one of his toys, and then created a mesh, and then you can animate, you can read the mesh, you can do whatever you want. And maybe so for more recent results. So that's once. So the advantage of Gaussian splatting is that you get a nice fuzzy rendering of complex surfaces. So if you create a mesh from that, then it becomes flat. It doesn't look. You lose the advantage of having Gaussian splatting. Here, the new thing, so that's basically we make the mesh populated with Gaussians to have more complex rendering. So that's here that's the kind of rendering that we get when we have a mesh. And here we combine the mesh, the advantage of a mesh and the advantage of Gaussian split. Okay, so that's the students who did the actual work. So the Antoine did most of the things that I presented today actually, and Chiao just started his PhD and is working on the indoor mapping. That's I presented at the second in the second part. Okay, so thanks a lot for your attention. I'm happy to answer the questions.
Thank you very much, Mr. Are there any questions from the audience? So for questions from the audience, you can either ask them or go to my. Yeah, the question I have is,
So semantic would definitely be useful. So for example, if we see that there is a door, we can imagine that there is a second room over there. I think the algorithm has the potential to do that because the shape of the door is probably characteristic and can probably learn something like that. I think the real problem with the indoor scenes is that there is a lot of dead ends in the environments. So that's something that we do not observe with outdoor environments because there is always a path to go back to something interesting. But because it's more complex, so indoor environment, so that's it's more complex and you have just a few paths that can be used to go back to a place. So that's also what is difficult. So this greedy aspect. But I fully agree with you. So something more semantic would definitely be useful. Thanks.
yeah.
So definitely, actually, the reinforcement learning is supposed to do that because we can we can give it some time, and at some point we compute the final reward. So there is a finite horizon, so that potentially it can do it, it can solve it. It's just that it's super difficult. So you have plenty of policies. I think you have a lot of attractors, a lot of local optimums in terms of policies. That's actually very strong. That's yeah. So that's it's difficult to imagine a good objective. Which is actually super interesting because that for humans it's supernatural. So that you don't have to teach anything. So it's natural to first scan this room and then go to the next room. If you don't want to hard code too many things into your learning algorithm and still learn something useful, it's not completely clear. It's not straightforward to formulate the problem. So especially for if you have maybe we can imagine some curriculum learning starting with small environment and larger, and then going to more and more complex. I don't know. So more and more complex environment, because that's if you have a very large scene, it's super attractive for the algorithm to go to go crazy and scan a lot of things. Actually, you can see, so that's the outdoors. That's also what the algorithm does. It's less problematic outdoor, but first it does a very large round around the building, and that it has to go back to get all the details. Yeah, no, so what we do, so we integrate, or we sum over the points that are in the field of view of the pose that we want to evaluate. So that's and plus there is the camera history in the input as an input to the G function, so the ones that predict or give at the end the gain over the surface. So there is this first the fact that we consider only 3D points that are inside the field of view, and plus the history that gives a little bit information about where the camera is pointing. So since because we sum over points, we can run the architecture as in a batch over all the points, so it's relatively efficient.
Yeah, please go ahead.
Mhm. So so for example, for the volume, so for the f function, we can compute the after a while we have a real volume, so not probabilistic, but the basically a binary volume of the inside of the scene, basically what is behind the surfaces that we have seen so far. And so we use, I think we simply use a binary cross entropy of over that, and so naturally is going to predict a probability even if it's the training data is binary. And that's because it's just train a lot of things and then it average over the different training samples. We should check back the papers, but I think it's a few minutes. It's relatively efficient. Oh, that's okay. It's also because the student is super good. He worked a lot on making the architecture efficient, but it's possible. Yeah, so it's possible to do it relatively efficient. So it's also because we sampled just a few poses around each pose. So basically, we have something like 6 samples. So every time step, we have to evaluate our networks only something like six times, or so that's which is basically the slowest part. The code is definitely available. Yeah. Sorry, say it again. Yeah, sorry, I miss, so that's, yeah, we would like to have a trajectory which is not too long. So that's, okay, so the first goal is to make it work, even if it's not optimal. And then, yeah, so that's, we are still working on making it more optimal. It's definitely not optimal yet. And think about even if you know the scene in advance, to define the trajectory which is optimal, that's also difficult. Ah, That's it's maybe there is a trade-off here. It's true. Sorry, access to? Ah, okay. For the indoor environments, so there was a question about semantic, so that's that could definitely help. So that's so we are interested in digital twins. So maybe, and when you are interested in digital twins, mostly when you have out of distribution buildings, I would say. So that's something a little bit different. But no, putting more prior would probably help. And that's yeah, that's true.
Any other questions? Yeah.
We
thought about maybe how
using what?
multiple.
Ah, yeah. Yes. So that's that's a swarm of drones. Yeah. So that's that would be super interesting. I guess one thing at a time. That's but yeah. So it would be very cool. So to turn the drones to communicate. So that's we are not experts in robotics, so we are really considering the vision problem. I guess so. People in robotics would have, because there is a full literature on swarm of robots, but that would be super interesting.
Yeah. I guess like I have to follow up this question. Not multiple drones at the same time. Let's say we should do a drone right now, and then later another drone.
Mm.
How are the results going to be flying?
So that would be interesting, maybe to check if things change between the two scans. So then that's where the second part of the workshop would be useful in terms of localization, I guess. So that you have a first scan, and you can that so from the first drone, and then use localization, robust localization, to localize the next flight. That's
And maybe it would be a follow-up question from my end. Thanks for the great talk. I think what is going in this direction is about like how robust is the gain function itself. Because like, let's say if you were thinking about you would like to map a larger building, and you map it in the morning, and then you come back in the afternoon, and the lighting changes differ. Like how robust is the gain function itself against those changes?
Yeah, so we don't use the RGB data as input. We use the depth maps, so it's more robust to this sort of things. So that's yeah.
Okay, then I might have another question. Maybe this is not true, but I'm wondering, for example, if you have more fine-grained or more ambiguous structures in the surface context, maybe it makes sense to capture more data of this error and somehow also encode it in the procedure.
No, not at all. So we have a hyperparameter that defines the level of details. So that's that we capture, but definitely, so that's if you have a nice sculpture, so that's maybe you want to spend more time. Definitely. That's so there is so from the depth map there is a sampling which is happening, and so we can control a little bit the level of details, but it's done okay, not necessarily perfectly.
Okay, and maybe have one last question regarding the post sampling. So you're mentioning that it's kind of independent of the control part, but I'm still wondering, like, if you sample poses, how do you like make sure that it's kind of consistent with the control of the drone? Like, if you sample arbitrary poses in the vicinity of the drone, and the drone control kind of like reach that, is
no, so that's something that we do not consider at all. So we sample close to the current pose. So you can have some motion model to make sure that these poses are reachable by the drone. but it was already done, okay, as a computer vision people and definitely not as as robotics people. So that's very,
Yes, thank
very
you.
simplistic. Okay.
There's one question from the Zoom audience by Fabian Schmidt. Did you think about integrating the generative approach? It could be generated like views from unseen areas of the scene that could then be incorporated in the planning process.
No, so that's there was actually a question or a similar question. No, definitely. So that's it depends what you want to do. Maybe if it's generative, maybe it's going to invent stuff. So that's which may be good or maybe not good. So it would be good because it would be faster. Maybe that's also dangerous. That's but so yes, Antoine and another student working on diffusion, they were interested in that. I was a little bit reluctant. That so that's, but maybe we didn't have the right ideas. Maybe there is something more to do there.
If there are no more questions, I would just want to ask one. I would be interested in like how large scale can the scene be in general? Is there like any limit in terms of the capacity of the model, or can you more
So in principle, so for the gain function, there is virtually there is no limit, but I guess there is some. So that's the advantage. So it's a little bit like a nerf in the sense that you can probe this volumetric representation by using a 3D point as input. So it's not like an array or something like that. But maybe there is okay, there are probably some limits, of course. So
Is there any other questions from the audience? Okay. Then I would. Okay, please go ahead.
so that was exactly that's but so that would be super interesting, super fun. But we are so that's there are people more expert in swarm robotics than us, but that would be super cool. Yeah.
Okay, there's one question.
Even when the 3D model is known, to find an algorithm that's going to generate the optimal trajectory is still super difficult. That's we don't. I don't know. I don't know if there is one. So I mentioned so this data set. So it's not online yet. I hope the problem is interesting enough to attract. To attract more people. So basically, that's the 3D scenes that we generated. So if you know the video game Doom, so there is a lot of the culture is still huge. So that's it's okay. So that's and there are generators, there are leveled generators, and so basically we can generate an infinite number of scenes, and you can see. So there are scenes that are super large. So that's and to find the optimal trajectory in this type of environment, that's even when you know the 3D model in advance, that's probably a super hard problem. But, so if you're interested to working on that, that would be.
Okay, with that, I would like to thank the speaker again for the great talk, and move on.
Thanks a lot.
All right, I hope you can hear me in the Zoom meeting.
Check.
Stop the video. Screen.
Yes, we can see.
Perfect.
Okay, so I'm happy to introduce our next speaker, who is Lukas von Sturmberg. Lukas is a computer vision machine learning engineer at Valve. Before that, he was working as a senior computer vision engineer at a startup Artisans in Munich, and he received his PhD in 2023 from the computer vision group at TU Munich. The research interests of Lukas, I think, are mainly vision and inertial SLAM, as well as the integration of deep learning approaches into classical SLAM systems. So we're looking forward to your talk, Lukas.
Thanks for the kind introduction, and thanks a lot for inviting me to this workshop. Now, currently, I work at Valve on computer vision, but most of this talk will be about the work I did during my PhD at TU Munich, where I had the pleasure to work with some amazing co-authors. I will talk about visual SLAM systems and how they can combine nonlinear optimization and deep learning. Now, modern SLAM systems oftentimes have an odometry component, which can track the camera in new and unseen environments, and also a mapping backend, which needs to perform some form of loop closure and sometimes relocalization. As for sensors, well, this is a vision conference, so of course images, but almost all commercial applications of visual SLAM also utilize an IMU because it is an inexpensive sensor that combines so well with the camera. Today, I will go all the way through this pipeline, starting with the work the MVIO on visual inertial odometry. So it will be about how to optimally combine cameras with an IMU. Afterwards, I'll talk a bit about how to do odometry only with cameras. Then there will be a part about loop closure and relocalization, and in particular, how to use direct methods with deep learning for this use case. And finally, I will talk about how the estimated poses, the poses estimated by a SLAM system, can be used for 3D reconstruction with the work monorail. Let's start with the MVIO. By now, it is very well known that cameras and IMUs are an excellent combination for visual SLAM. And in particular, the work MSCKF by Mourikis and Roumeliotis was very influential in this regard. But to get the best out of these two sensors, you need to combine them on a very deep level. And since I'll be talking about methods that are optimization-based, this level is the energy function that is being optimized. So typically, there will be a visual part to the energy function and an inertial part. I'd briefly like to explain factor graphs because I'll be using them a lot in the next couple of minutes. So with factor graphs, we can visualize the structure of an energy function. So the idea is to visualize all the variables of circles and all the sums with squares. So f is connected to x and y, and g is dependent on y and z. In this way, we can visualize the structure of the system. Now, in our system, in the MVIO, we're using nonlinear optimization to estimate the trajectory. And the first part handles the camera and is based on DSO, direct sparse odometry, which was developed by Jacob Engel, who will talk right after me in this workshop. Now, this photometric error simply says that if we observe a point from the different positions, it should look approximately the same. And you can see it depends on the camera pose for different frames that we have, and also on a number of 3D points in our scene. And from now on, I will leave out the 3D points in these visualizations. So this was the visual part. And then there's also an inertial part. So we add variables for the IMU, namely the velocities and biases. And we also add these green factors, these green IMU factors, which basically say that the motion from position 0 to position 1 should be approximately what our IMU tells us. And in practice, they're based on IMU pre-integration, which was proposed by Forster et al. So we can optimize this energy function, and the result will be a very accurate trajectory of our system. One problem that we addressed in particular is the problem of IMU initialization. because as most of you will probably know, with just a monocular camera, it is impossible to observe the scale of the environment. But if you add an IMU, you can observe the scale because the IMU measures the metric acceleration. But that's only what people tell you. In practice, it's a bit more tricky, unfortunately, because just imagine that your camera moves with a constant velocity. Well, in that case, there is no acceleration. So the IMU can't tell us the scale of the environment. And that means that in practice, depending on your trajectory, it can take an arbitrary amount of time until the scale actually becomes observable. So many other systems start with a visual-only system for that, and they run an IMU initializer in parallel. And once that IMU initializer is finished, they will initialize the visual inertial system. I'm talking about monocular methods in particular here. Of course, for stereo, you can immediately get the scale. But this introduces a trade-off when to initialize, because if you initialize too early, the scale might still be inaccurate and your performance might get worse. But on the other hand, if you initialize too late, your system will not be as robust as it could be. So in our previous work, the IDSO, we came up with a different solution. And the idea was to immediately initialize the visual inertial system, but then to jointly optimize the scale explicitly in our main system so that we can notify it when the scale changes. And then we also added a special marginalization technique to make this work in cases where the scale is very wrong initially. So the advantage is we could use IMU data immediately, but the downside would be that it would fail when did the microphone just?
No, this is the other one. That's fine.
I can also steal your microphone if you want.
Maybe it's easier now.
Does it work again?
Test 1, 2. Okay, perfect. Yeah, so what I was saying is that the advantage is that we can use the IMU data immediately, but if for like large scale outdoor scenarios, our initial scale would be wrong by a factor of like 20. So the environment would be 20 times as large as we think initially. And in that case, the system would fail because the difference would be just too large. And also the scale convergence could take a bit long. So for this follow-up work, the MVIO, the idea was to combine these two systems. So we use a separate IMU initializer, but we also still optimize the scale explicitly in the main system. And therefore we can initialize quite early, because even if our scale after IMU initialization is wrong, we can still compensate for that quite easily. It will work in general environments, and the scale will converge quite quickly once it becomes observable. So the factor graph from before is modified as follows. We add the scale and the gravity direction as optimization variables. And we also came up with a dynamic photometric rate to make this even more robust. But if we use this separate IMU initializer before the system, it introduces a couple of questions. For example, how can we transfer the knowledge that we gained about scale from the IMU initializer to our main system? And also what to do if the scale is still off over time. And we came up with this technique we call delayed marginalization to overcome both of these drawbacks. And the idea is that in addition to our normal factor graph, we also maintain a second delayed graph where the marginalization is just delayed. Because to keep the system runtime constrained, to keep it fast, we will marginalize variables over time. For example, here, P1 is marginalized first, and the result is a marginalization prior that summarizes the previous knowledge. And only then we add the next variable P4. And this continues over time. We always marginalize out a variable and then add back another variable. But as you can see in the delayed graph, we haven't started marginalizing yet because, well, the marginalization is delayed. So now the delay is reached, and the first pose is marginalized in our delayed graph. So one thing you might ask is, well, isn't this too slow now? Because we were marginalizing variables for a reason in our main graph, right? And if we just don't do that, don't we have a problem? Well, for the normal optimization, we still just use the normal graph as before. So that's just as fast as it was before. And in the delayed graph, we only perform marginalization, and this we can prove is just as fast as marginalization in the normal graph, no matter how large the delay is. Because you can see that P1 is only connected to these 3 other variables here, and that makes the marginalization procedure very fast. And that's because we don't just blindly marginalize the oldest pose first, like which would be P0, because you can see P0 is connected to all these variables, which would be much slower. But instead, we follow the marginalization order from the main graph, and that way we can guarantee that it's fast and that it has almost no overhead. So what can we do with this delayed graph? If we don't use it for optimization, well, what is it useful for? Well, basically, we have a larger optimization window at our disposal, which we can use anytime. So let's continue a bit. And for example, for IMU initialization, we can populate this delayed graph with IMU variables and factors. And then we can optimize this resulting system, which is a very good IMU initializer. And we call this optimization post-graph bundle adjustment, inspired from post-graph optimization and bundle adjustment. And this optimization is faster than bundle adjustment, but more accurate than post-graph optimization. And other systems will just assume that our visual poses are correct for IMU initialization. And this way we can capture the full visual uncertainty with no, the full kind of uncertainty. Another advantage is that this graph can also be readvanced, which works by successively marginalizing out the variables again. And the result of this will be a marginalization prior that we can use for our main system. So in this way, we can again transfer the full covariance from the IMU initializer back to our main system. And another thing we can also do is if our scale changes over time, we can use the same technique to later recompute the marginalization prior and update our first estimates Jacobians, which overcomes another drawback of marginalization. So based on these techniques, we came up with a multi-stage IMU initializer, which is robust even against long stretches of constant motion. And so we could apply it, for example, in the automotive scenario, which is quite hard on IMU initializers. Now I'd like to show you some qualitative results on the TumBI dataset. The bottom left, you can see the current camera image and the depth map. Here you can see the point cloud that is estimated by the system. And in red is the current camera position that is estimated. And in green, the current ground truth position. Right now, you can't really distinguish the two because they align still perfectly, but later on the ground truth will end for some time and you can see the difference. So now the person walks through the corridor. I hope you can see it well, and enters the Magistrale building in which is actually at TU Munich in our informatics building. And now you can see the person walking up the stairs. In this building, we actually have some slides that go down from the 3rd floor to the 1st floor. You will see the person actually entering these slides, which is basically a black tube with almost no visibility. But because of the IMU, the trajectory can still be reconstructed very accurately. And in the end, you can see pretty much the entire building being reconstructed. So one thing I want to highlight is that this method does not do loop closure. So in the end, you will be able to see the drift that has been accumulated because the person comes back to the starting position. You can see that even though this was a very hard trajectory, there's almost no drift that has been accumulated, just like 20 centimeters or so. Another example is the automotive scenario. And as mentioned, this is typically quite hard for monocular inertial methods because you see right now the car drives basically with constant velocity. There's no way to estimate the scale yet without deburring. But because of this IMU initializer, it still works very well for this use case. This is actually the Four Seasons data set, which was recorded in Munich. So you can basically see the Munich inner city right now. I might scroll forward a bit towards the end of the trajectory. And here you can see the scale of this trajectory that is estimated. And again, the car will come back to this original position. There's no loop closure, and you can be able to see the drift. If you look closely, you will see a bit of height drift here. If you look towards the bottom, bit of height drift, but compared to the size of the trajectory, it's quite minimal. And of course, it's also important to perform quantitative evaluations of these methods. So we've evaluated this method on 3 data sets, capturing flying drones, handheld scenarios, and automotive scenarios. And we were able to get quite some good results. So we were even able to outperform very popular stereo inertial methods, even though this method only uses a monocular camera and an IMU and no deep learning inside. The source code for the MBRO is published on GitHub, including some evaluation tools and also a ROS driver, so you can use it in your robotics applications. And there's also a live demo, which we've shown at IQA 2022 and also the Bavarian AI Day, and that live demo is also open source. So this was some of the work on visual inertial odometry. And now you might ask, hey, so the system is very robust if you add an IMU to it, great. But what if you don't have an IMU? This is a vision conference after all. So this is what this work T3VO is about. And this work was led by Nan Yang, by my colleague. And in this work, deep networks estimate the depth, the pixel-wise uncertainty, and also the relative pose between 2 images. And all this information is then fused into a traditional optimization-based odometry system. And the results were also quite good. So compared to state-of-the-art traditional methods from the time, they had quite a hard time on Europe, which is very understandable. Europe is a very hard data set for monocular only methods. And these are some great methods otherwise. But this work was able to perform quite well on it and even perform similar to state-of-the-art stereo inertial methods from the time with just a monocular camera. And what I find quite cool about this is that the pose that is predicted by the network is estimated in a very similar way as how the IMU is integrated in the previous works. So in a way, deep learning almost acts as an additional sensor and is integrated in a similar way into this optimization-based system. And this kind of shows how in SLAM, deep learning oftentimes does not replace optimization in traditional methods, but they are combined to achieve the best results. So of course, once you've built your map with odometry, you would often like to reuse it and relocalize in it when you come back later. And that's what this work GNet and LM-Relog is about, which was developed in close collaboration with Patrick Benzel. So the SLAM methods that I've shown previously were all direct methods, meaning that they work directly on the pixel intensities. And that's part of why they were so accurate and why the reconstruction was relatively dense. But direct methods also have 2 drawbacks. First of all, they need a good initialization, because otherwise the optimization does not work. And secondly, they cannot handle strong lighting or weather changes. And this, of course, these 2 things are problematic for relocalization when you don't have good initialization and the lighting changes a lot. And therefore, before this line of work, relocalization was mostly done with indirect methods. But in this line of work, we present some neural networks to overcome both of these drawbacks. And we were able to show localization results across different weathers. I'd like to start with explaining a bit how direct image alignment works. Let's imagine you have an image I, and you wanted to track it against image I prime from the map. Then you can get a sparse depth map from an odometry system like DSO, and using an initial solution for the rotation and translation between these 2 images, you can project the point into 3D and into the other image and get this point P prime. And if our solution for this pose is good, then the brightness difference between these pixels should be as small as possible. And you can do this for a number of points. But if you look closely into this image, if you zoom in, you will see that the point positions don't quite match up yet. And that's because the initial pose was not fully correct yet. But the idea is that we can optimize this energy function using the Gauss-Newton or Levenberg-Marquardt algorithm. And then we would expect that these projected point positions get better and better as our estimate for the pose gets better. Now, this is a bit simplified, but in principle, it is how direct image alignment works. Simplification is, in practice, there's a Huber norm here, there's some affine brightness corrections, but in principle, this is how it works. But of course, for these two images, it won't work because they come from different daytimes and the brightness changes will be too severe. So we propose to replace these images with deep features that are generated by the neural networks. So we still use the same point depths estimated by DSO, and we also still use the same energy function. We simply replace these images with the features F. And these features are trained to be robust against illumination changes and should work in this kind of scenario. But how do we train them to have these kind of properties? Well, we train them using ground truth pixel correspondence. So we have a data set where we know, hey, this point corresponds to this point. And as a loss function, we propose the Gauss-Newton loss. And to explain it, you have to take a closer look at what happens when you run direct image alignment. As explained, you will usually start with an initial slightly wrong solution for the pose. And starting from there, the Gauss-Newton algorithm will estimate a Gaussian probability distribution for where it thinks that the correct correspondence will be. So here it thinks the correspondence would be here with this kind of uncertainty. So not quite correct. And this is done for all the points. And together, these 2D probability distributions determine the update step for our rotation and translation. Now, the idea of this Gauss-Newton loss was to work directly on these probability distributions and to simply say, hey, we want to maximize the estimated probability of this ground truth location. And that way, the network should learn something useful. So in summary, this was designed to specifically work well for this Gauss-Newton algorithm. But for our follow-up work, LM-Relog, we wanted to go one step further. Because we observed that for direct image alignment, it's actually not usually the Gauss-Newton algorithm that is used, but the Levenberg-Marquardt algorithm. And Levenberg-Marquardt is basically an interpolation between Gauss-Newton and gradient descent. So for example, as long as the solution is far away, like this orange point, you expect that this algorithm behaves like gradient descent. And then as you get closer, it should be more like Gauss-Newton. So the loss formulation that we came up with is specifically designed for this and considers 4 cases. The first one is that the point is already at the correct location. Well, great. Then the residual should just be small. So we take the ground truth correspondence and say, hey, the features at these locations should be as similar as possible. The second case is, hey, the point is an outlier. And then we would like the residual to be large to reflect that. So we sample a random negative point across the entire image and say, hey, the features at these locations should be less similar than a margin M, which is in practice a hinge loss. Third, the point is still relatively far away. And then all we want is that the gradient points in the right direction. So we sample a point in a relatively large vicinity, like, for example, here. And then we compute a gradient update step, which is this yellow point. And then we say, hey, the distance from this yellow point to the correct solution, the distance after the update, should be smaller than the distance was before the update, which would mean that we made progress and even better than some judgment. And then the last case is, hey, the point is already very close, which would be this red point. And then we would like to converge quickly. We assume it's Gauss-Newton algorithm. And for that, we sample a point in a very small vicinity, like this red point over here. And we just compute the Gauss-Newton loss, which I've just explained we designed for this use case. So notice how all 4 of these loss functions use a slightly different way to sample the points involved. And in our results, we found out that all of them were necessary for us to get the best results. So here I'll show some results on our relocalization tracking benchmark. And this is a cumulative plot. So like 7% of the images were localized with an accuracy better than 10 centimeters, what this point means. So the more to the top left you are, the better. And clearly this benchmark is quite challenging for normal images, which is very expected because it's just not what it's meant to be used for. But if you just replace images with deep features trained with a standard contrastive loss function, you already get much better results. If you then add the Gauss-Newton loss, you get even better results and also more accurate results. Then in the follow-up work LMVlog, we were able to improve the parameters of the method a bit. So same loss function, but better parameters and got slightly better results. And if we then add the full LMVlog loss function, it gets even better. And so we went one step further afterwards and said, hey, we also employ a post-estimation network. So a deep network that just gets to images, estimates the relative pose, and we use that as an initialization to it. And then we were able to get these results. So this kind of shows how in this line of work, we were able to go from images being essentially useless for this use case for direct image alignment, to direct image alignment being actually quite useful for relocalization. And here are some qualitative results for that. So here we relocalize the snowy sequence, which is this blue point cloud, against the map taken in sunny condition, which is the white point cloud. And the idea is that as long as our tracking works, these point clouds should align well. So in the beginning, they align well. And if that continues over the course, then it's good. And in the bottom row, you can see here the current image, the closest map image, the current features, and also the closest map features. And if you focus on the lane markings, you can judge the accuracy. So one thing that I want to highlight is that unlike most other methods for tracking across different weather conditions, this method does not need repeatable key points and 3D locations for them. In fact, we reuse the 3D points from DSO, which are highly non-repeatable, and they can be on lines, on lane markings, on shadows, on everything. And this is something that I quite like about direct image alignment and related techniques, that we can use all of these kinds of points. Forward a bit. Oh, well, never mind. So that was some part on relocalization, how to reuse your map. Does the microphone still work?
Seems like it's off again.
Oh, it's off again.
What again?
Yeah, it's off again.
Did you fix it?
Maybe I'll just
Yeah, maybe just.
I'll just steal that microphone. I hope you can hear me well again. So another work that I would like to highlight is MonoRep, which was led by Felix Wimbauer. And this answers the questions, well, what if you want a denser reconstruction of your environment? Because these point clouds look, I would say, nice, but they were a bit sparse. So this work leverages deep learning to generate this kind of more dense reconstruction of the environment. And one reason why this point cloud looks relatively accurate is that it utilizes multiple frames and combines them in a cost volume, because this is a monocular method. And to do this, it takes the poses from a monocular SLAM system or odometry system and combines them, as I said, in a cost volume. So using multiple frames can make moving objects a challenge. So you can see some moving objects that would make this reconstruction less nice. So one novelty in this work is how we filter out the moving objects. So there's a new mask module which predicts where moving objects are and removes them from the cost volume straight away. Then afterwards we filter. So this, what you can see here, is Dawn, a state-of-the-art monocular depth estimation network from the time. And you can see it's quite impressive what they're able to do with just a single monocular image. But still, by using multiple frames in a cost volume, we're able to get a bit sharper reconstructions. So even if it's just one single monocular camera, the temporal stereo helps a lot, of course. So this also shows how monocular SLAM can be used not only for robotics or virtual reality or augmented reality, but also to get these nice and 3D reconstructions in a second step. This is again a moving object. So of course, nowadays, these might look less impressive because there's NERV and Gaussian splatting and some really, really exciting progress in the field. But one thing I want to highlight is that this work is, well, first of all, it just simply reprojects the points from the camera to 3D with the estimated depth. And it's also mostly real-time capable. So this reconstruction can run at 10 frames per second. And I think that's also because we separate this task of pose estimation and of dense reconstruction. And I think sparse point clouds are already very sufficient to get really, really strong results with SLAM. So I think this can still make sense to separate this out, even though we've also seen some really exciting papers on how to combine that. And so it's kind of an open question if that's a good approach. So this was some of the work that we've done at TU Munich. And now I'd like to end with a couple of words about Valve, where I currently work on computer vision. So many of you might know Valve for video games like Half-Life, Counter-Strike, Portal, or Dota, or for Steam, which is a gaming platform on the PC that connects millions of players. But Valve also makes hardware, like the Steam Deck, which you can use to play PC games on the go, and even a VR headset, the Valve Index. Now, in the hardware team, we're really invested in computer vision and in its role in future technologies, and we're looking for more people to join our team. We're local here in Seattle, and our office is just across the lake in Bellevue. So if you're interested, just scan the QR code and it will guide you to the job posting on our webpage. Or feel free to talk to me or one of my colleagues during the next days when you see us. Thanks a lot.
Thanks a lot, Lucas, for this great talk. Are there any questions from the audience? Yes, I would recommend going to the mic. It's easier to follow. Thank you.
Hi, great talk. Can you give a more details about how you generate this mask?
So again?
How you generate the mask with the clean object?
Let's see if I remember. So I think if I recall correctly, we generate the cost volume and concatenate the features and then put them into a neural network that estimates this mask. And I think one of the core novelties was a loss function where we basically leveraged the fact that we expect the static stereo error to be lower for moving objects than the temporal stereo error. And then we also utilize some form of instant segmentation for it. The detailed architecture is in the paper.
It's supposed to the pure instant segmentation network.
It's a bit different. So we only use the instant segmentation at training time. And at runtime, we only use this mask segmentation, this mask module.
So how do you separate the concept of the foreground and background to the somehow like the motion oriented foreground and background instead of a visually semantic foreground and background where you can get directly from the instant segmentation?
So I think we took the classes and the objects for the instant segmentation and then utilize some specific other formula to find out which of these are actually moving. So I think for this, we actually used this trick that static stereo should be more accurate than temporal stereo for these. So that way we created some ground truth for it and then trained based on that.
Okay, I will check the paper.
Yeah.
Thank you.
Hi, thanks for the great work. I have a question about the relocalization.
Mhm.
So it seems like from your video that it's relocalizing while driving along the same distance. I'm wondering if you have any comments on how well you work or what challenges with the visually are very different.
Yes, that's a very good question. So of course, this kind of direct image alignment with deep features has still some limitations in terms of the baseline, in terms of how large it is. Because while we were able to clearly boost the performance when the initialization is bad, at some point there's just a limit, right? So for these kind of use cases for autonomous driving, where it's maybe a couple lanes to the left, to the right, this works very well. If you have like crazy different viewpoints, of course, then indirect methods will work better for that.
One follow-up. So have you tested like driving, just even in the other direction with that?
This is something we haven't tested. I think it would be quite challenging, to be honest. And in general, that's actually quite a challenging system. If you look at some state-of-the-art SLAM systems that are out there, I think they also have a hard time if you move forward and come back. And this is actually, I would say, kind of an open question, let's say, to integrate a SLAM system that can do really loop closure from crazy moving forward, moving backward. So I think that's an interesting follow-up work in general.
All right, thank you.
The NPL work is really great. It's amazing. We've looked versions on large scale. It's quite impressive. So besides the delayed versionalization and initialization, what practical advice would you give the community on making integrated, IMU factors work? Is it something that you paid very close attention to that really was a secret to making that work?
I think it's honestly a lot of engineering work and just getting all the small details right, because I think in SLAM, if you make a mistake, it oftentimes doesn't break, but it just works slightly worse. So you just need to have a lot of attention on detail. Actually, what I used also, which is great that you asked the question, I used your system GTSAM quite a lot in this work. And one thing that I didn't, that I would like to highlight also is this kind of combines kind of this backend optimization from DSO, which is very optimized and hardly optimized, and it's hard to work in, but at the same time, it's much faster. And I combined it with GTSAM for the IMU factors and the other things. So in a way, you can use this also to have very fast photometric errors, but still use GTSAM and get the flexibility. So that helped me also to not do everything myself and reuse things.
First of all, the postnet is the post generated by the metric scale or relative scale?
We tried to estimate the absolute pose, if I recall correctly. So really the absolute pose, which of course is very hard because we don't give the network depths. So it's a pretty hard task. And this network is not very accurate, and it's not the goal to be very accurate because we just need it as an initialization.
And
so,
I'm curious about how to guarantee that the scale is very consistent across the sequence.
You mean for the relocalization or for, okay. So, well, we utilize the points from DSO, so for our SLAM system, for the main optimization for this direct image alignment, and just gives us the scale pretty much of this relocalization.
Yeah, really great presentation. There's a follow-up question regarding the postnet. So it's my estimating the state down between two images will be very challenging. Problem is that the estimated scale from that make the problem easier.
You mean have a network that estimates the scale for you?
Between two images.
That's, I'm not quite sure what you mean by the scale. You mean, I think it's similar to the work, how D3VO uses the network to estimate depths. So if that's what you mean, so that's actually also related to like the IMU work, because what also can be useful is, I said with a monocular camera, you cannot observe the scale of the environment. Well, with deep learning, you can, although I consider deep learning more as like an additional sensor almost for that. So that's what D3VO uses a lot, that it uses these estimated depths, and that way you get a nicely scaled trajectory.
Yeah, because based on my experience, asking the network to directly output the system is very fragile and it's very not accurate. Just want to see if you have seen.
Yes, so my experience is more in the way that asking network to estimate the 60 degree of freedom pulse is very robust, actually. It will not give you very bad estimates, but it is not very accurate. And that's why it's so nice to combine that with nonlinear optimization, like for this, just using it as an initialization. Also for the 3VO, where we basically use it to give it a prior similar to the IMU, and then the result will get much more robust, the resulting system. And well, for accuracy, we have optimization.
Okay, thank you. I have also a second question. So the second question is about the loss part. You mentioned that 4 different or 5 different kind of components. One of it is to sample some negative. So because I mentioned a lot of examples are easy negative, how do you kind of make sure that you can have some really meaningful negatives so the loss can learn from it?
I know that a lot of works use hard negative mining for that, but for this work, we actually just picked the random negative one, and it also worked quite well.
I noticed that all of the methods direct geometry, we're really separating the mechanics of wells that are campus.
And what again?
Mechanics of wells that are campus.
Oh, yeah.
I'm curious if you're allowed to talk, you thought significantly about mitigating problems. Of course, you've got the industry, both campus and wells are.
Yeah, so we do have one paper on like visual inertial odometry with rolling shutter. The main challenge for these kind of things is runtime, however. because we don't, unlike indirect methods, we don't like first compute correspondences and then can correct the rolling shutter, get the line. Here we basically have to project points from one image to the other, and then we can check the line, and then we see, oh, actually our pose was slightly different, then we need to project it again to find the actual line and do that iteratively. So we found that runtime performance is a challenge for this. So I would say having this really real time and applying this to rolling shutter is kind of an open challenge, which would be interesting to work in.
Question about how do you think about the faster?
About what?
Faster, the transformer framework which directly takes 20 minutes as input and use point out and
I have to admit that I haven't read the Duster paper yet. That's on my reading list, so unfortunately I can't comment too much on that yet.
Why did you not look at it?
Any loop closure? I didn't have time to do one more project in my PhD. It's a short question, so I worked on loop closure techniques, but this is not included. And the advantage, of course, is you can use more data sets. For example, the TOMBI data set only has ground truth in the beginning and in the end, where you start and come back to a mocap room. And with odometry, this is still very good for evaluation because you can evaluate the drift in the end. But if you have loop closures and you do a loop closure just before the end, that kind of defeats the purpose. So focusing specifically on odometry and first making this work very well, I think has a lot of value.
Makes sense.
I would also have a question to you, Lucas. Thanks for your impressive work. I have a question regarding the initialization of the NVO. So how sensitive is the system in terms of calibration, for example, IMU camera calibration? Have you done any like practical considerations there? Because as soon as you touch hardware, it's become complicated usually.
Yes, so I should say generally in terms of calibration, this is a very sensitive point for all these direct methods. We assume a very good calibration. For IMU camera calibration, I did not have to optimize that for these data sets, but in the code, you will see that it's very much prepared for optimizing the camera IMU calibration. And you can do that like from the initializer and then also so all these techniques for IMU initialization should also benefit this IMU camera calibration. And pretty much, I would also only have to enable a flag there and then tune the priors for it and try it out. So this would be actually a very easy follow-up work in terms of that.
One slight follow-up question is, do you have any experience on let's say, using a low-grade versus a high-grade IMU? And like, how does it affect the performance of the system?
So I did notice that, for example, for this live demo, which I use a RealSense T654, I did notice that the drift was a bit larger than, let's say, for these TOMBI data sets and these other things, which I think is because the IMU is not very high grade and also the camera. And especially the frequency of the accelerometer was just 60 Hertz instead of 200. So I would say it definitely has some impact. Still some great hardware, by the way, sorry. Yeah, I would say it has some impact, of course.
Okay, thank you. Are there any other questions? There's one.
I have a question. So I noticed when you use the video for the localization, when it comes to curvature, I noticed that the fractal was a bit off. Is that something that you noticed, or is there a reason for the difference? Because you had different speeds, or
I didn't notice.
Okay,
oh, yeah.
You maybe go to the mic. That would be great. Thank you.
So my question is, if we look at the video here from localization, I noticed whenever we have curvature, usually the tracker is a little bit off, more off than straight line. Is that something that you guys have noticed?
I didn't notice that too much, to be honest. I would have to check back. I'm not sure. Of course, the accuracy depends a bit. It can also be that because, let's say, the point clouds come also from slightly different times, right? So it could also be that some shadows on the one side or on the other side of the building. So I would have to check it more detailedly. I would say it looked relatively accurate, but also didn't notice that much difference.
Okay, with that, I would like to thank the speaker again. You can follow offline. We have a coffee chat now. So we have a coffee break now for half an hour, and we will reconvene at 11:10. So 10 minutes after 11, we reconvene. See you. Yeah, no, I think can we maybe press next to the mute arrow? Yeah, and then to like the settings, the last one. And I think we untick the automatically adjust button and just like did it like first. Yeah, I think that would be good. Great, like this. Check videos for maybe turn off the speakers. If someone uploads their screen, or do you share screen by I think you can share a screen. Sorry. I have no idea if it's working. Okay, let me check. Yes, all right. Like everyone, we will continue on that session with our next speaker. Our next speaker is Jakob. He is the director of research and Localization, who is leading the egocentric machine perception research as part of the development project RLO. He has over 10 years of experience working on SLAM, and environment. Leading goals, research program, as well as technology to better any results from the University of London in 2016, and he is currently methods for the SLAM to use for and LSD stuff. It's a great today.
Thanks, Patrick, for the introduction. Yeah. We are entering the age of AI. Just about 2 years ago, that would have been a somewhat bold statement. But within the last 2 years, I think we've moved so fast that this is basically now what everybody talks about. And nobody disagrees with it anymore. However, I'm going to argue in this talk that actually localization and mapping, and more broadly, egocentric machine perception is, can you all hear me?
Great. Went out before again, and we tried to fix it, but is it work? Now they all died. Yeah, we had the definition in, but he couldn't fix it. Now it's back, is it? No.
I just maybe turn it off and on.
Yeah, good idea. Try turning it off and on again. That always works.
Switch it on.
Can you press it on again? Is it back now? No. So it's not back. Yeah, we just had the issue before, but to come back as well. No.
Yeah, this one works. All right. Well, I'm going to try this one and hope that one doesn't switch on as well.
No, it's I'm sorry.
All right. Well, wonderful. Fantastic. Well, yeah, so much for the age of AI. Let's say we still have some way to go. Okay, but more broadly, right? There's a general paradigm which I think is useful to just come back to every once in a while, which is that any ML model is only as good as the data it's trained on. And in fact, in the last couple of years in particular, we've seen an extension to that, which is that any ML model is only as good as the data it is trained on or has access to, right? Like one of the big things we've seen over the last couple of years is that LLMs in particular have learned how to effectively interact with digital systems, with APIs, write code, and can access data not just through the training data that they were trained with, but also more broadly by searching the internet, by making function calls, by literally using tech as we humans would almost use it. Right. So how does that data look like? Well, if we look at LLM agents today, probably the biggest source of information it has access to is all the world knowledge that we've put on the internet over the last 30 years. It's trained on that, right? We're moving from only being trained on text to also images and videos and all the other good things, but effectively it's the repository of human knowledge that we've put online over the last 20, 30, 40 years. Second, more and more AI agents are going to have access to personal digital context. So that's things like your email, chat, calendar, information, documents. And you see that happening through various companies integrating LLM technology into their operating systems or products as we move along, and actually using the APIs to interface with that. But then third, I think there's a third important piece of information to make AI agents truly useful or agentic, which is physical context. So that's everything around you, how you're interacting with it now or in the past. And I want to argue that physical context, this third bit, is actually necessary to make personal AI assistants really useful in the future. And that's because all these questions I put on the slide, right, starting from things like where did I leave my keys to who did I talk to or at the conference, I don't remember the name anymore, all the way down to well, what can I cook tonight with the stuff that I still have in my kitchen. Really cannot be answered by ChatGPT and similar things today because they don't know any of the answers to that. There's actually an analogy to that. So if you look at human memory, the explicit human memory can roughly be broken down in two categories of knowledge. First, there's semantic knowledge. That's basically everything you know about certain things in the world, right? Like, you know, apples, you know, they're edible, they're fruits, they have stems, they're sweet, they cost like 90 cents a piece, whatever. And then there's the second part of explicit memory, which is episodic memory. So that's everything you remember about certain things that happened in the past, experiences you had, who you talked to about what, where you left your keys, whether you have an apple in your backpack right now. All those things are grouped under episodic memory. And right now, the reality is that AI agents have a lot of the left, but none of the right, right? They know everything about apples, but they don't know whether you have one in your hand right now or one in your backpack. Okay. And I think we're going to solve that through egocentric machine perception. And I actually think this is one of the growing fields across the community, including obviously computer vision as one of the major senses that play into that. Okay, so I'm a bit loose with the term egocentric personally, although this is sort of depends on what exactly how to define that. It can mean things seen from the viewpoint of a human. But I also think it applies to robots, right? Basically anything observed from agents in the world, whether that's a human or a robot, doesn't matter. All counts as egocentric. But in this presentation, I'm going to talk about machine perception from the viewpoint of humans primarily. Okay. This one was a bit obvious, but I do think that localization and mapping in 3D is actually the basis for always on egocentric machine perception as a key input for contextualized AI assistance in the future. And there's two reasons for that. First, it provides the basic spatiotemporal structure for effectively episodic memory, or the AI version of that, which is what happened, where, and when. And then two, it allows to fuse and compress sensor information to save compute and exploit redundancy, right? Like if you look at something, you don't see it like one frame at a time and you re-identify what's there every time over, but you can actually fuse things over time and exploit the fact that you're living in a 3D world. Those two are actually somewhat complementary. So the first one mostly relies on coarse, global, and low-frequent localization, maybe semantic localization, right, like what happened in my kitchen, maybe even moving things like what is in my backpack. It's a very broad interpretation of localization. And then the second one is fine, local, and high-frequent. So that one is really what allows to effectively fuse information in 3D over short time intervals at very, very high precision. Okay, so how do we go about that? At this point, I want to introduce Project Aria. It's a research device built by Meta to accelerate machine perception and AI research. It's a pair of glasses. It looks like this if you take it apart. It has a whole bunch of sensors that are useful for machine perception. It has a high-resolution RGB camera, 2 monochrome SLAM cameras, eye tracking cameras, an array of spatial microphones. 2 IMUs that we've heard about are very, very important if you want to do any localization really reliably. And then a number of other useful things like barometer, magnetometer, Wi-Fi, Bluetooth, GPS, all the good stuff that you'd use to actually get localization solved for good. It doesn't have a depth camera. I'm going to come back to that. It also only weighs 75 grams, which means you can wear it fairly comfortably over a long time period, and it can record data for up to an hour. I do want to give a heads up just because it gets frequently misunderstood. It's a recording device only. It doesn't have a display. It's not AR glasses in that sense. It doesn't have on-device compute. It's really a tool for research to effectively capture egocentric data, the egocentric multimodal data, and work with that. Right. How does it look like? Here you can see an example of an RGB stream. These are the 2 left and right SLAM cameras. They have quite a bit of peripheral vision to eye cameras, and then the whole array of other non-visual sensors, microphones, IMUs, and barometer, magnetometer, thermometer, and some other ones. All right, I'm not going to talk too much about it. It's a research initiative. You can engage with it if you want to know more about Project Aria or how to get a device or what data set exists. Please come visit us at the Beta booth. So, in addition to being a recording device with all the sensors that especially this community will appreciate, I think, we also provide a whole bunch of basic machine perception capabilities that is not useful to build on top of. And I put them on the slide here. That 6 of location, point clouds, eye gaze, palm and wrist poses, as well as very high accurate calibration, sensor models, and time synchronization across all the sensors. So if you want to run VIO, this is actually a very, very good device to do that. I want to talk a bit more about this. Under the hood, we call it machine perception services. Really, it's a pipeline where you can upload a recording and you get back some results. It's unfortunately not open source currently. It runs a couple of things. It runs a VIO front end, actually very similar to a lot of things that Lucas talked about earlier. It gives you an output and an open loop trajectory and online calibration of all the sensors. Then we run a SLAM mapper that does nothing. And afterwards, we bundle multiple maps from multiple recordings all together in one joint map. And then that gives you poses for all the frames and all sensor measurements at a high rate in a common coordinate frame. And last but not least, we run a semi-dense tracker. Again, this is very similar to what Lucas talked before. It's a derivative of DSO that I worked on at TUM. That computes high accurate metric point clouds. Okay, how does this look like? So here's just an example image or video that you can see it's somebody walking through an apartment with an Aria device, and you get all poses, you get nice point clouds, you get these semi-dense step maps. And it all looks really nice. And throughout the rest of the talk, I'm going to talk about a bunch of projects that actually build on top of this. One thing I'm going to call out is that calibration or online calibration really matters. Here's what we do in the lab with Aria devices once in a while. You can see that even though we try to build it as rigidly as possible, you can only make it that rigid within that weight constraint. So it is a bit non-rigid, and online calibration does account for that. Okay. So this CVPR, we're actually publishing 3 new data sets that are all built using Project Aria. And they target different communities, but what they all have in common is that they all attempt to bring egocentric machine perception into 3D using localization and mapping underneath that. I'm going to briefly talk through all of them. First off, there's EgoXO4D. Probably some of you have heard about it already. This is a very, very large scale data set consisting of egocentric and exocentric recordings with hundreds of participants across hundreds of environments, across 15 cities worldwide. It has 5,000 takes and over 1,400 hours of video combined across the egocentric and exocentric views. This comes with the basic machine perception services output, which are metric point clouds, eye gaze, and camera poses, which you can see here, for example, from the cooking video I showed earlier, right? Like this is the point cloud, the eye gaze, and the moving camera frustum. And you know, here's another example from a climbing trajectory, and there's a bunch more. UX also defines a bunch of benchmark tasks, key step recognition, ego acceleration, ego pose, and the body tracking from the egocentric vision, and proficiency estimation. So I wonder if you can tell which one of these two climbers is the expert and which one is the novice. So yeah, it enters you know, a whole community of effectively action understanding, ego pose estimation, but all with data that is localized in 3D, so you can use these signals and solve all these tasks in 3D if you want to. The second data set is the mirror data set. This one just came out on the weekend, so it's very, very new, and it's about human motion in the wild. It's again a huge data set of in the wild human motion. Contains about 300 hours of everyday activity, everything from walking around the house, cooking, cleaning up, biking around a campus. It's very, very diverse. Hundreds of participants, 50 different locations, about 3,600 hours of video. And some nice additional stats. It contains about 400 kilometers of head motion and about over 1,000 kilometers of accumulated wrist motion. So it's a very large data set that contains all of the ARIA data as well as full human body pose ground truth. So you can learn how humans move in the context of the environment they're in. We built it using a Xsense motion capture suit. It's a suit with lots of IMUs that allows you to effectively estimate how you're moving. Gets used in Hollywood quite a bit. As well as ARIA devices and a slightly modified ARIA device that fits on your wrist that we use for wrist tracking. Here's an example just of the diversity of this data set. So you can see people doing all sorts of things, swinging around, doing exercise, playing ping pong, cycling. It's really, really a very broad collection of what people do during everyday life. Just an example of how some of the videos look like. So this is a video from the right wrist while somebody's playing badminton. So if you want to have fun with challenging sequences for VIO, this is a good example. Films a lot of sky, contains a bit of collisions. But yeah, it's an interesting example, a snippet from this data set. The other thing I really like about it is that it aligns all this data that's collected in the same location into one global metric coordinate frame. So what you can see here is an example of just one house out of 50, and all the trajectories from about 8 hours of activity that happen in that one house, right? And this is just head and wrist. Obviously, all of this comes with full body pose as well. In red, you can see the head motion. In blue, you can see the right hand. In green, you can see the left hand. And you can see how just from the trajectories, you can actually see motion fields of what happens where. That are incredibly dense, again, just from about 8 hours of somebody doing stuff in this house. There's a couple of zoom-ins. There's a kitchen, you can see like head moves in the middle and then the arms kind of like reach out onto the countertops very frequently. Here's a bit of a pop quiz. Can you guess what this kind of object is? What are those green and blue arches? It's like red left hand and right hand. How do they move like that? All right. This example is a fridge, so you can see us the left and the right hand opening the fridge door. Here's another example. What are those blue arches that kind of are curved a bit downwards and take place at some place in the living room? Put an arrow there to give you a hint. Opening the window, no, darts. I've heard darts, fantastic, yes, there's somebody playing darts. So you can actually see the dartboard on the other side, right? And then you can see the trajectory of throwing towards the right hand. Right, next area, Hot 3D. Hot 3D is a data set about hand and object interaction. So this is, again, a large data set, 800 minutes of video, 33 objects, 19 participants, 3 different environments. It contains perfect ground truth for your hand motion, your eye gaze, and then object motion and CAD models for these objects as well, which you can see rendered here in the middle. It's collected in 3 different scenarios, approximating like an office, a kitchen, and a living room. It has 33 distinct objects that come with very high quality models for those objects, so you can render them to generate training data if you want to work on like 60 object pose estimation. And it comes with high quality ground truth from OptiTrack. This data set is also going to be used in 2 challenges that are both going to take place at ECCB later this year. One is the BOP object tracking challenge, and the other one is the hand tracking challenge at the HANDS workshop. So yeah, check out those websites if you want to learn more. Again, actually, both those challenges tend to be on monocular images without sort of camera motion or egocentric views, and this data set helps to bring both of those into a 3D world. All right. Last, we don't just build data sets, but we also use them. In fact, we build them because we use them, because we need them for the machine perception research we do. So I want to give you a quick overview of some of the work we do at Spatial AI in Surreal. First up, human motion model learning. Sounds kind of obvious, right? Human motion isn't arbitrary, it follows common patterns, can be learned, right? If you remember the maps I showed from the Numera data set, you can definitely see patterns there, and they can be learned. So some work that we did 4 years ago is called TLIO, Tight Learned Inertial Odometry. This is just estimating human head motion from just an eye view. No cameras, right? The video I'm showing here is just for visualization. And the output is a odometry trajectory. It effectively learns how humans move and combines that with the signal from the IMU to get a head trajectory that is reasonably accurate, about 1 to 2% drift in good cases, but obviously if you do some crazy stuff like jump around, lie down, some of those things are out of distribution and it won't work that well for those. More recently, we've also combined that with VIO, similar to some of the things that Lucas talked about, where traditional VIO actually can be extended with ML quite well. Here's an example of a really, really challenging sequence of VIO where the cameras are basically almost dark, and actually, at some point VIO just brutally fails. You can see on the right. However, on the left, what it's showing is a gradual transition. Whenever VIO is too ill-constrained to continue, it'll transition over to use the motion model instead, and then transition back to use VIO when the cameras are useful again. And obviously less accurate, but it still allows to track really, really challenging sequences like this all the way through with vision and IMUs. Here's another example. We get a lot of these kind of videos. People wear hats, and hats are really bad for HMDs. This is a person wearing a hat and walking on the beach. So at this point, you basically see the hat and you see the water waves coming up on the beach, which just means you can't use vision at all anymore for tracking. However, again, the motion model takes over, continues the estimated motion while you're probably still walking straight, and then transitions back to VIO. So again, right, like on the left, you can see roughly the right trajectory being estimated, mostly a straight line walking on the beach, and on the right, it just brutally fails, keeps resetting. No way to like relocalize or track with vision only in these cases. Right, next, we're going to extend this principle to the entire human skeleton. Right, it's not just about heads, it's also about everything else that you have on your body. And here's some work we can call motion prior diffusion. It's currently under review. The input is, again, just an IMU from the headset and an IMU on the left and the right wrist. And from that, we learn a model, it's like an offline diffusion model, so not exactly real time, that will estimate the trajectory that you moved as well as your full skeleton motion. And you can see it actually working quite well in this video here. White is the ground truth, green is the estimated motion. But when the person starts making some weird motions, or stops just walking and doing standard things, but starts like sitting down, you can see it fading quite badly as well. So there's still some work left to do here, but it is severely under constraints, right? There's just 3 IMUs, 1 on your head, 2 on your wrists. All right. Here's another work, HMD2. This adds in the obvious thing, which is that your motion obviously is correlated with the environment that you're in. So the environment-aware motion generation from an HMD. In this case, the input is the full 6 of trajectory from the headset, as well as the RGB images, as well as the point clouds to get like a geometric understanding of the world. And the output is again full skeleton pose and orientation in the world. And this works extremely well. So if you look on the left, all those blue, purple skeletons are actually body poses estimated by this algorithm from the input I just described. On the bottom right, you can see the ground truth. And in most cases, it's very, very similar. It even works for quite crazy motions like kicking a ball, where just the fact that you're looking at a ball, which you can see in the RGB camera, and then the head motion that comes from you moving your feet actually allows to estimate that your leg is kicking. So this is really, really impressive, and actually quite astonishing how much signal there is just in motion models for humans. All right, next up, structural and semantic mapping. It's all about identifying objects around you and build a map of what is where. But the project I want to talk about here, we published it sometime early this year, is scene script. The idea here is to tokenize a scene using the latest and greatest and hottest stuff, which is autoregressive transformers that spit out language. So in this case, the input is a point cloud. Again, right, just a semi-dense point cloud that comes from effectively DSO and ARIA MPS, as I talked about. What gets encoded, then gets decoded using an autoregressive transformer into a language that contains commands that generate walls and doors and windows and bounding blocks of things in the scene. And the output looks like what you have on the right. Here's an example of that approach actually running on Quest, on a Quest device. Walking around a bit, you get a point cloud of the scene, you see the semi-dense points, right, not an dense point cloud. Press a button, it takes about 3 seconds for this model to run. And it would generate a reconstruction, a coarse reconstruction of the walls, the windows, the big clusters of objects, the doors, and so on. The nice thing is because it's a trained model, it's actually quite flexible. So you can use the same mechanism to train a model that decomposes the point cloud of a room into walls and floors and bounding blocks of big things and doors and windows and so on. Also use the exact same approach to train a transformer that now decomposes individual objects into geometric primitives like cuboids, cylinders. And you can see that on the right here, where all the chairs and tables are approximated with some kind of geometric primitives in fancy colors. Right. Next, we're also looking at egocentric foundation models in 3D. So obviously, foundation models in 2D computer vision have absolutely overrun the field. The idea here is to come up with something similar, but natively in 3D. Take as input multi-camera video, as you get from ARIA, camera trajectories, because we still think actually computing that explicitly is usually a good idea. The same semi-dense point clouds, stuffing all of that into a big model, and then get a representation that you can decode into surfaces and bounding boxes and all the other good things you might want to know about 3D space. Here's the first version that we also published just earlier this week, together with the idea of egocentric foundation models called egocentric voxel lifting, and it effectively lifts all 2D foundational features into a 3D grid using camera poses and scene ray geometry from the calibration, concatenates that with point clouds. Runs a fairly straightforward trained 3D unit, and then can be decoded into voxel occupancy and bounding boxes of objects in the scene. It actually works really, really well. So what you can see here looks like your everyday, RGBD scan of an environment. However, it's not. This is really just a reconstruction created from the ARIA device, right? 2 monochrome cameras, one RGB camera, and used for tracking, and it gets you a really good reconstruction. This is still running EPL on like short snippets and then fusing them using standard TSDF fusion and some filtering for the bounding boxes. And just to make that direct comparison, right? Like on the left here, you get a reconstruction from an ARIA device, again, no depth camera, from walking through a scene once using EPL. And on the right, this is from the replica data set in the same room from, I think, 4 or 5 years ago, using a fancy RGBD scanner with high resolution cameras and walking throughout the scene to like capture every viewpoint well, as people do today still in many cases. And the quality is frankly, the RGBD scan is still more accurate, but otherwise it actually looks very comparable. Because this is just from an ARIA device, you can run it on much larger environments as well. So here's an example of using the exact same approach on an entire office building. This is about a 40-minute trajectory of walking through, I think, 5 or 6 floors of a building in London. And you can see on the left side the point cloud, and on the right side you can see the dense mesh created using EVL. And it's pretty impressive, right? Again, this is just 40 minutes of somebody walking with an HMD through that building and getting a really accurate 3D mesh of at least the areas they have visited, obviously not the entire building. Some ongoing work, so we're also looking into segmenting that better into bounding boxes and rooms and big objects like doors, windows, chairs, couches, tables, storages. So here's a video of the exact same input recording walking through an office building, but identifying bounding boxes of all the different objects around. Mostly it's an office building, so there's a lot of chairs and a lot of tables. And then if you're fancy, you can start overlaying that. I think the microphone broke again. All right. Well, enjoy the video.
Yeah.
Hey.
Hi, but like it's happening all over the time again, and we don't know what.
Just like.
Yeah. We already asked the technician, and he didn't know to check it.
All right, I was just going to rewind to here so you can see it again. But instead, I'm moving on. Okay, but you can start seeing how things like this actually provide really important context for AI assistants, not just on what you're doing, but also what is where, right? Where is your desk? What did you leave on your desk? And so on and so forth. I'll bring you to the last part. So, tracking interaction with objects. So far, we've talked about human body motion, right? We've talked about environment reconstruction, frankly, static environment reconstruction, right? Nothing changes in any of those environments. But in reality, things change, right? Like you move things around. And that's in particular true for egocentric vision, where it's from your viewpoint, and humans tend to move stuff a lot, all the time. So humans move the way forward, and actually what you do with objects around you is one of the most important signals you can get for AI assistants. Okay. The other thing I want to mention here is that, right, like there's a lot of work going into reconstructing static scenes. It's very, very hard to update them when changes happen, in particular when sparse changes happen, right? Like not everything changes. Most things stay the same for a long time, but some things do change, right? You move a chair here and there, you move some small object, people get up, right? Like this room will look mostly the same in an hour, but not exactly the same. Okay, so how do we do this updating? Well, the key thesis here is that actually humans move the world. So a lot of the changes, in particular in your home, for example, are caused by you. So if we track how you interact with the world around you, that actually is a perfect way of updating reconstructions, or at least knowing where you should update them. So here's some other ongoing work on exactly this. Tracking is a system that uses hand tracking and object detection and so on to effectively track all the objects that you interact with and localize them in 3D space. So here in this example video, I just picked a video where somebody takes a lot of stuff out of the backpack, right? So objects appear. You can see the objects appearing, both with that like little gimmicky tetrahedron, I think it is, floating over them on the table. But then also it builds up a library of all the objects you've interacted with over time. That again is super useful context for AI assistants, right? Like this will answer you where you left your keys just fine. Here's a slightly more complex example. So there's a person walking around a table in an office where we put a lot of everyday objects and just moving them around. And you can see on the right just a map that initially is empty, but every time an object gets moved, it pops up in the location where it is moved to. So over time, rolling up a map of the environment, and you can imagine if an object already is there, pick it up, it disappears, and so on and so forth. All right, putting it all together. So before I wrap up, I want to leave you with a view of all of this put together. Because all of this is just using like ARI device data, we can actually run it in the same sequence. And it looks like this. So this is a human motion, right, with full body skeleton motion, walking through an environment that's being reconstructed in 3D at the same time, detecting bounding boxes of objects and so on. You also get these little floating icons that are items that the person's carrying around with them using the dynamic indexing approach I showed before. And over the span of 40 seconds right here, we basically get a fairly complete reconstruction of the person's apartment, where the objects are that they interacted with, and so on. I do want to mention here that this is a slightly cherry-picked example. So a lot of these methods, right, like are very much work in progress and don't work as robustly out in the wild. So, finding a recording where all of them work just fine. Is not that straightforward, but you can definitely see the path how this becomes a path to get, contextual signal for AI agents in the future. They'll not just know everything that's on the internet. They'll not just know what you wrote in your last email. They also know what's around you, how your flat looks like, what item you put where you left your key, where you put your backpack, and so on. And again, all of this just estimated from a lightweight pair of glasses, although using a couple of GPUs in the backend. So we're still got a bunch of work to do to getting of this run on real time on the device, so it can actually be used to practice effectively. All right, with that, on to questions.
Amazing work. I mean, the amount of progress made in the last couple of years is just staggering. Scene script, in particular, is shocking and even upsetting in a way. Yeah, you proceeded to show a bunch of other approaches that do essentially similar things. So I basically am interested in the dirty laundry here. That's like, why do you see scripts for all that stuff? And what are the downsides? Yeah, and if there are no downsides, how does it work? Maybe you can't answer that question either.
I think I'm going to mention two downsides. Like one, the way it's built, it's a batch process, right? You take in a point cloud of a room that has been accumulated over some time. You run a network, and you get a floor plan level reconstruction of the environment with some geometric primitives for objects. But it's very hard to update, right? It's a one-off thing, and it actually starts working less and less well if you start using it on larger environments. So you can't run it on an office building, right? You'd have to split that office building into meeting rooms, then you could run it on the meeting rooms. That's actually what we did in the video that I showed, where I had those white boxes around meeting rooms, right? But it doesn't scale very well. So that's reason number one, and there's obviously various ways to go around that, including fancy ML techniques that now put things into sort of vague variables that can access again and so on. And just system approaches, right? Like segmenting things and running it on rooms when you do them. The second big challenge, I think, is the thing that all ML methods have. It's limited by training data. So the scene script is trained on a massive data set of 100,000 procedurally generated environments. So we wrote a script that places objects, assembles rooms, renders sequences in them, did that 100,000 times. The data set is actually online. It's called ARIA, synthetic environments. And it works great in any kind of environments that look like that. It doesn't work in environments that don't look like that, right? So it would have a hard time in this room, for example. So yeah, that's the other big downside.
Talk, and like Frank mentioned, it's scarily good. But I have a bit of a let's say, a meta question, which is you shown a lot of work on those data sets, and I wonder if you could share some sort of like a key insights over your work on generating those data sets. Like, if you could share some thoughts on like what is the thing to create a good and successful data set for the community?
The key thing, you are the one who wanted to use it.
Okay.
Very simple answer, right? Like, honestly, the best data sets are created by people who want to solve a research problem. And it turns out they need the data set to solve a research problem, because that means you know what you need. And you build the data set that way, right? I could give you lots of technical answers, but that's the biggest one that I could find, right? Like the mirror data set with the full body human motion wasn't entirely built not because we wanted to build a data set, but because we wanted to solve the problem of egocentric human pose estimation from egocentric data. And it turns out we didn't build that data set. So that's the biggest one. There's lots of other things, right? I'm going to go into all the technical ones.
That's a really
Are there more questions? if you have. So clearly this work is really deeply coupled with the hardware that you're using. And I was curious sort of what hardware updates are you waiting on the most? What are you most excited about in the next few years in terms of like what's getting better and what's going to really change the space for you? That's a good question. I think there's quite a bit of leeway on just IMUs getting better. I think part of the reason for that is that a lot of the IMUs that we have today were built for smartphones and developed for smartphones, right? Like IMUs built for like HMDs, high quality, high fidelity tracking, have just started to be developed over the last like 5, 6, 7 years. And it takes a long time to develop these things. That's number one. Number two, I think, is just power and size. So, right, like even ARIA glasses are frankly still something that I would not wear personally out in the wild, right? They're too big, they're too clunky, they cost too much power. Just the lenses of the cameras are too big, right? So there's real physical limits there. So yeah, making sensors smaller, lighter, and use less power.
A great presentation. I have one question regarding the multimodal. So now we only just maybe some voice, or maybe you tell LLM you're doing some kind of activity, and you can identify what kind of activity you do by have some audio information. How will that potentially what's your plan integrating all of them together to make it advanced?
So just like data sets to do that, right? Like the narrated, ego narrated data sets. And there's a lot of value in that because you basically get for free in situ annotations about what the person was doing, right? You text it, speech to text it, and you get narrations. I think from an application perspective, what we're looking at is assistants that work while you're wearing them and not paying attention to them, which means that, you know, the idea that you constantly tell it what you're currently doing is exactly what we want to avoid. So from an application perspective, we're trying to get away from like the person having to like constantly tell the person like, now I'm giving a presentation, right? Now I'm trying to get a coffee. But from a data set perspective, actually, it's a great way of getting annotations.
I think it's a very amazing work. So in the slide, I'm wondering about the question. So in the slide, you present that the human motion actually is not arbitrary. And it evaluates that you use an annual and the actual work and use annual to predict human motion. My question is that I think how do you exactly program the on stage actually? For example, I think it really depends on the training data and if it's on the same moments, how do you exactly how do you adapt for that motion? I think that is a very good challenge.
Yeah, I mean, like in the last bit of the video I showed, you could also see the human skeleton like going off a bit crazy. So yeah, it's a very, very ill constraint problem, right? And you never solve that with more and more training data, just regularizing it to output like an I don't know, or like a default pose. Or you can do actually what I think is the more practical way, which is to integrate it with other data, right? You got like this is then the other work where you add some camera images, you add maybe a trajectory because you don't just have the IMU. Maybe you know something about the environment because you've been there before, right? Like you have a scene script reconstruction, which means now you know where your legs are because you know where the floor is, and so on, right? So I think there is we need to use these other signals.
Got it. Thank you. I think I just have a big follow-up question. You think using like simulation data sets can trigger like a motion model that can maybe apply to the real world environments like humans?
So the question to really use data sets to learn good prediction models.
Yeah, for this huge motion. That's
Some of it yes, but on another level is actually really hard, right? Because you would need whatever generates that data set to actually already have a very good motion model of humans, otherwise they couldn't generate it, right? So you got a bit of a chicken and egg problem there. There's certainly the next step, right? Like if you have really good language models that, you know, run on thousands of GPUs offline, you can use that to generate data sets to like train more real-time algorithms, things like that. But otherwise, when it comes to simulation, actually studying ground truth or synthesizing human motion, especially, you know, relative to objects and so on, is a really freaking hard problem. And frankly, the way people do it is they collect real world data and then like retarget it in various ways.
Question, like a question about privacy. So obviously, egocentric vision data reveals about like personal being and the human life. How do we deal with privacy? For example, if you think about like 3D reconstructions, like all the and so on.
Yeah, really, really important question. So it's right? Like for our itself, because it's a research device, like we put a lot of things in place to ensure privacy, like face blurring and things like that. But that's just for research. And then for any kind of real world application, I think the crux of it is going to be, well, all of this has to be 100% private, 100% personal, right? Ideally, actually run on your device or on your phone, so it doesn't even touch any kind of cloud compute, which is the safest way to make sure that things stay private. But yeah, you're right, like, I mean, same as your emails and your chats are private and really should stay on your phone, the same applies here. Which, you know, makes the whole argument of all of this has to run on embedded compute ideally, right? Or at least with like less compute power, all the more important.
We will have a small 2 minutes lunch break, and we will be five the one. See you all. Thank you. Ja, auch gemacht. Bei der Audio-Settings, wenn du auf den Haken drückst, auf Audio-Settings, ganz unten. Genau, wir hatten immer, wenn du ein Stück nach oben gehst, nochmal, sorry, dieses Automatically Adjust ausgemacht und die Input Volume auf ganz hoch gemacht, weil die Leute haben sich beschwert, dass man es schlecht versteht. Das ist besser. Vielen Dank. Good. Okay, hello everyone. Welcome back to our afternoon session. I hope you had a good lunch break. We're directly going to dive in with the next keynote talk, which is from Peter Conchita. He is Director of Research Science at Meta in Zurich. Peter received his PhD in 2013 from Graz University of Technology. His research interests include computer vision and machine learning, in particular with focus on photorealistic scene reconstruction, semantic scene understanding, image-based 3D modeling, and generated modeling for 3D synthesis. Yeah, we're very much looking forward to your talk and the safety skills.
Thank you. Okay, good. Thank you everyone for the organization, for the invitation for me to have this opportunity to talk about some of the work that my team and I have been doing in our lab at Meta in Zurich. The title of my talk is More Ingredients for Mapping the Metaverse. Let's see what kind of impression this will leave with the audience as we proceed. But it's really all about, well, talking a little bit about the kind of direction and vision that we've been pursuing for quite a while with my team. And the North Star is really kind of unchanged, which is develop the next generation of computer vision and machine learning algorithms so that we can really provide kind of high fidelity, high quality environmental reconstruction results, scene representations that are holistic, that allow us to provide like a holistic understanding in terms of semantics, but also in terms of the structure of environments. And we want to build that purely from images at some point, and we want to leverage this for building a really immersive experience in the metaverse. Let me show you what I'm referring to. So this is essentially a video that we've been recording with some of our devices. It's a Quest 3 device. And I will just try to look through or beyond the initial kind of phase of this video. What you see here is essentially somebody exploring in a very immersive way, a radiance field directly rendered, not on the device. Unfortunately, this is in a tethered setting, but the experience is real. And when I tried this myself for the first time, I thought, I think we're onto something here. I think this is really something that can be a key moment when you look at the fidelity, you look at the fine-grained details, you look at the kind of reconstruction results that in VR really all of a sudden induce this feeling that you are in this other environment, even though you're not, that you want to, maybe hold on to something or like grab a chair or grab something that's shown in this environment. And having this photorealistic impression really makes a key difference as opposed to this kind of more toyish or cartoonish environments that we've seen in the past. There is a downside. So on the right-hand side, what you see is the kind of capture device that we used here. It's called the Eiffel Tower. We've released a data set captured with this monster. It has 22 cameras on it, and it's quite a little bit of a challenge to actually capture full environments with this type of recording. So we're clearly not done, right? What we want to build instead is a metaverse or a form of representation for the metaverse that anyone can contribute to, right? Anyone should be able to take their phones, use their like devices, their VR headsets with their cameras, and really scan their environments that matter most to them, so that people can bring those type of environments into VR and maybe invite others over. So, what we show here is essentially one of these recordings that somebody was making with a smartphone. This is in Zurich. It's called the Swiss National Museum, and it looks like a fairly high fidelity and fairly realistic reconstruction for a space that anyone could capture with their mobile phones. And this data set is a data set that we're storing on Mapillary, and Mapillary, for the ones who have been familiar with that project, it's a street level kind of data capture platform where anyone and everyone can contribute with their phones, with their devices. What we're trying to do is like solve the reconstruction problem at super high fidelity also for this type of heterogeneous data. Good. So it essentially breaks down to 3 key ingredients. And those ingredients are obviously data. So we've looked at this just now. We really want to support any kind of domain. Could be images, videos, could be also multi-modality data. But for the sake of like simplicity, let's just focus on images for now. The other form is we really need a strong representation. So that representation needs to be efficient. We need to be able to render it efficiently, to model it efficiently. We also want to have chance to like model dynamics in these kind of environments. And obviously the corresponding algorithms that we're building, they should be robust, they should be insensitive with respect to the kind of aberrations that we typically encounter with these type of data environments. But before we dive in, we need to get some prerequisites. So I will not go into like the details here. I think most people are familiar, and this is something that really has been around for a while now. But it all actually started with like image-based 3D modeling a very long time ago. And what you get here is if you like have images that are unposed, you can run things like structure for motion, you can get like a point cloud, you can do multi-view stereo and then densify this a little bit. These are kind of fairly well-known techniques. They are working well, but probably not good enough so that we can just throw any piece of data at them, so that we can kind of retain the kind of parameters or like the output that we would want for the subsequent step, which is the photorealistic neural rendering. But they're pretty robust already. There is a caveat, however. So if you're interested in like pushing the boundaries also of image-based 3D modeling, I think there's still a long way to go there, especially since there's the strong dependency for building neural representations in terms of accurate camera poses and pose information in general. On the other hand, we have given some form of good quality pose information and high density data capture with like good coverage and like good local kind of understanding of the scene. Then you can build those neural radiance fields, which essentially allow us to like incorporate this information into the form of like density field or the form of color field, and then re-render for a novel viewpoint and run novel view synthesis there. The second chunk of prerequisites that I'm making here is we want to have a form of understanding about object recognition. And object recognition for scene understanding really helps us to assess the data that we take in input. This is stuff that we've been like very dedicated a couple of years ago, and we've spent a lot of effort and energy into building well-performing object recognition models that could, for example, run panoptic segmentation. Panoptic segmentation is the task of, like, for example, you take an input image, like the one here, and you want to decompose it into like things that are called things and stuff. And things are like, for example, all the countable objects in those images, which could be pedestrians, could be cars, and so on. But we also want to get a background. And the background is essentially amorphous areas, which could be the sky, which could be the road, which could be sidewalk, and so on. So stuff that we can't count. And what you see here is essentially one of the models that we published about maybe 2 years ago. And we thought, it's kind of robust enough. So this is like giving us a decent kind of output. We are probably close to this form of like diminishing returns. So we thought, okay, let's try to make use of this algorithm and see what we can do with that. And at the same time, we also invested into monocular 3D object detection. It's like shown here on the bottom. Essentially, you get a single input image in RGB. And as output, we want a 3D bounding box in camera coordinates. And what we also want to obtain is essentially like the extent of the box is the rotation, the distance with respect to the camera. And then what you can get, and this is something that we published at ICCB 3 years ago, was given this monocular input image, you can get these 3D bounding boxes. The visualization here is really just leveraging the LiDAR for a better form of presentation. And now we have all of a sudden like a couple of tools in our hands. We have the image reconstruction, we have the nerve, we have these types of object recognition algorithms that help us to like move on. So what are the challenges that we're looking at? So I've briefly mentioned Mapillary before. So Mapillary is this open street level data collection platform, if you want, where anyone with a device like a mobile phone, or maybe even with a professional rig, all types of different like capture devices are supported, where you walk around or drive around. And this is the kind of data that people upload. So it's really driving sequences from a dashboard cam here, and you can see that there's essentially a lot of like dynamic stuff in there. There's not really a lot of control on the data capture itself. It's really, really challenging. This is in the wild data that we care about solving and like integrating for the kind of tasks that we want to like ultimately pursue. So for some of this data, we've been trying to extract and build like very thorough and comprehensive data sets. And one of the data sets that we've been building is the Mapillary Metropolis data set, which is like a city scale 3D benchmarking data set where we have still sparse point clouds for an area of a few square kilometers from Detroit. And the goal essentially here is to have a bunch of image modalities. So we don't just have like high quality 360 imagery that we capture there, but also a ton of heterogeneous data that people were collecting like alongside this project that doesn't necessarily match with all the structure and like the information that we have in the high fidelity scans. We pair this together with human annotations in 2D, in 3D, with LiDAR point clouds from the camera, like from the vehicle camera, but also from aerial LiDAR sources, from multi-view stereo, and all in all trying to build a really multimodal and comprehensive data set that we can leverage for like moving the needle on this project. So given all this data, Mapillary and heterogeneous data, what's the next step there? Are we just done now? Can we, just run it everywhere? Well, obviously not, no. The challenges really are getting more and more the closer we look at this data. And while novel view synthesis or nerves have this wonderful like functionality or feature that we can run novel view synthesis to get a high degree of photorealism, or we are able to model view-dependent effects or reflections or things that are really very difficult with traditional methods. But there's also more downsides here. So all the dynamic things in there are really challenging. Even swaying like trees and branches and like all the dynamic information is usually something we don't want, right? And this is what you probably remember if you've or what you probably remember from looking at a lot of the neural reconstruction results, that people typically filter this out, this content, this information. So other things, super picky about the camera poses. So we remember from before, if the sparse reconstruction that gives us the camera pose information, if that's off, then most likely you will end up with something that generates a lot of floating artifacts, a lot of undesired reconstruction artifacts that really don't produce this high quality representation of the work. So if we start filtering like all of the things, all the dynamics in an area like the time square, just to show here, there's still a ton of floating information there. The time square is super, super busy, right? So if you want to do something challenging, download this data from Mapillary, everything is publicly available there, and try to reconstruct that scene and make it look like really, really nice. I'll pay you a beer if you manage. So what we tried to do instead was finding some supportive data. Is there ways where people were like capturing in a more friendly way that's helpful for us, like on the left-hand side, right? So some people tend to be very thorough when they do mapping, which is really appreciated. So if you go out and map, please be thorough and like capture every single piece of the environment in a very thorough way. But we can also leverage the semantics, right? So we can use the segmentation models that we've shown before to isolate the sky, to isolate all the moving stuff in there. And if there's enough capture, then there's a good chance that we've seen maybe some of those pieces or some of these locations that are previously blocked from a dynamic object, that they will be seen later on, and we can still have a decent chance to reconstruct this. So with all these types of like constraints, we actually managed to successfully launch NERFs for Mapillary just earlier this year. So we've been like receiving a couple of submissions that were recorded with a set of different instructions that we're sharing with people to like get the optimal kind of result for the NERF reconstruction. And now we are we currently have a couple of dozen reconstructions on the Mapillary platform. And this is a feature that everyone can contribute to and hopefully help us grow on the database that we have. And some of these results are shown here. So people are really in very different locations and in different places. And just again, just remember that this is really from consumer devices. This is not something that leverages a strong and powerful rig setup, which obviously would be better suited. But at the same time, very few people have that account. Good. So let's come to some of the other challenges that we're looking at. So NERFs are usually good at reconstructing things whenever you have like high density of coverage, 360 coverage for different objects that you want to model. But what if we go in this setting where we are looking just at a single shot, novel view synthesis from like a single input image, and that's from a street level setting. So what we did here was essentially assuming that all we were given is a single input image, like the one here, and then we could apply our object recognition algorithms to disentangle the scene into the semantics, like on the panoptic segmentation, you can see the different color codings, but also the 3D boxes that kind of give us a better form of 3D understanding. And what we showed like 2 years ago at CVPR was this AutoRF paper where we developed this model that helped us to essentially, from a single input image only, derive still a 3D object instance and object information that allows us to do novel view synthesis from a 360 perspective. Quickly going over the details here. So again, this is our input image. We decompose this into like the individual instances. And what we then do is we have a way to like run those individually separated instances through our encoder setting here that gives us a shape code and appearance code. And at the same time, we're able to leverage this kind of normalized coordinate system here. So, or this normalized coordinate space to actually squeeze in the information that we get for every single instance into this like unit cube, so that if we just have enough viewpoints and enough kind of observations from different angles across the entire data set, we can leverage the space to actually complete the entire shape and learn a corresponding like information about the shape and about the appearance. And then during rendering, what we can do is essentially we can decode the corresponding shapes, and we can decode like a chosen appearance information. And from that, we can re-render novel views from different viewpoints, and at the same time add different color information. So we can just recolor also the instances there. What you see here is essentially a form of qualitative results. So we've been training this on new scenes, and we test the same model that we just trained on one data set on different other kind of data sets in the output. And given these nice kind of individual images, all of a sudden we can turn this into like essentially a full animation where we can change the car shapes, we can change the car appearances, and have like a much better understanding of how the world would look like in 3D. So the next project that I'm talking about now is, can we do better? So what I'm showing here is a video that was a part of the Block Nerve paper, which was presented 2 years ago also at CVPR. And this was a really interesting kind of moment when we saw that there's a way to reconstruct larger scale environments and show larger scenes. But if I just stop at an arbitrary point here, what you can see is, so all of those streets are empty. There's not even the parked cars out here, right? So the instances, all the dynamic instances are fully filtered out here, which kind of leave a little bit of a like, sad impression of the world, right? So what we're looking at is, can we do better? Can we have a way to actually model a scene as part of their static components, but also as part of their dynamic components? And before we dive deeper into that, let's take a little bit. Let's take a look at the kind of data that we're using for benchmark. So here we derived this benchmark setup, which is part of a paper that Tobias Fischer was the lead author, and I just see him back here. So hi, Tobias. That we also present here at CVPR this week, where essentially we're leveraging the Argoverse data set, which gives a very good kind of representation about what we also have available at Mapillary, right? So there's different sequences that we are recording in the same geographic area. The different series that, you know, there's also very good kind of additional information about the cameras that are used, the additional like sensors like LiDAR. So this happened before in the morning session. Don't worry. I hope at least. Yeah, needs to breathe a little. So we have this benchmark data set, and on top of this, we've been extracting a couple of like sequences and data from sequences that would be helpful for us to assess, can we do this joint modeling of static and dynamic environment parts? All right, so what we're doing is essentially, we're given a set of different sequences S here, and every single sequence has a couple of objects associated with that sequence, right? So, and all those objects, if you look at this kind of hierarchical graph that we're building here, it's essentially kind of comprising or added as part of each sequence. We have this information in terms of the timestamps, in terms of the vehicle poses, in terms of the camera and the calibration information. And so this is a way how we can essentially like build up this information from different sequences that we have for the same geographic area. At the same time, for each of the objects, we have the pose information with respect to the ego vehicle, and we also have the object dimensions. And again, if you think back of what I showed earlier, if you have an off-the-shelf 3D object detector, you can essentially assess this kind of information or infer this information with that. And now the final kind of goal is we want to estimate again a radiance field. And that radiance field should give us again a density and some form of appearance information. But this time it's also conditioned on the, like not only the location, but also essentially on the time and on the sequence. Good. So what we do next is we essentially build up this scene graph information, and you can see this hierarchy again, where the graph consists of a couple of nodes and edges. And within those nodes, we have a way to, like, again, address the different sequences. We have the latent codes, which are helpful for modeling the appearance information. And this appearance information, again, could change because the sequences could be recorded at different times of the day, different times of season, and so on. So we are able to like absorb all this information here and have a fairly well-structured form of like establishing this graph that helps us to represent the scene from the corresponding type of data that we've captured. And now the goal is to essentially like model the entire kind of function that we're interested in as part of a static radiance field, which should take care of the background information and of the dynamic and foreground radiance field. And the really nice thing that turns out from here is that you're able to like render novel view trajectories by really combining and matching and mixing very different information across different scenes, which is really cool. So let me show you just the state of the art from last year, which was presented at CVPR last year. So you can see we have a little bit of a challenging novel view kind of trajectory that we impose on the camera. And the results are like really, really like not ideal. There's a lot of floaters, there's a lot of artifacts. And it's because this is a really challenging model or challenging data set as well. On the other hand, there's obviously a solution. For the same trajectory, you can see that our model is actually doing a lot better. It's not perfect, especially if you look at, for example, this car from this side, but this is also because we haven't really observed this particular viewpoint for that car very often. And at the same time, you can see that all of a sudden those static environments now turn into something that look much more realistic because we can also start incorporating dynamic information there. Another thing that I briefly touched before is that now we can do mixing and matching, right? So remember, there's multiple sequences that we've been leveraging for building the initial kind of graph. And all of a sudden, we can now change appearance codes. So we can make it brighter, we can make it darker, we can make the different cars combined that we've observed from different recordings. And I think it's a really new and interesting direction that we're looking at. Of course, we also have a number of experimental results, quantitative results. We've been testing this on this Argoverse benchmark data set on the top. And you can see that with respect to the baselines, we have quite a sizable contribution on top. And we've been also testing this on top of the Kitty benchmark data sets, the real one and the virtual Kitty data sets in this case. Of course, all the details and the papers. There's also a sneak preview for something that we just released on Archive, I think a week ago. And you can see if we are able to model the environments with a more recent representation, which here we are based on Gaussian, 3D Gaussian splatting. You can see that the results look actually even more crisp. There's even more fidelity, even higher fidelity that comes out of these models. Again, a lot of the details and all the experimental analysis, also comparisons with respect to our CVPR paper are within the Archive submission. Good. So let's go a little bit back. Right now, so we have a little bit of a better understanding of what we can do in terms of modeling of static and dynamic outer environments. But we really don't have a full understanding of what it means to have this information about the instances also baked in as part of the representation. So what we've been doing here, and this is another really cool project that we've been working on with some of our interns a while ago. It's called panoptic lifting. And the goal of this project was, given 2D segmentation information, is it possible to reconstruct fully panoptic 3D neural radiance field or volumetric representation from only post RGB images? And the kind of reason why we want to do it is, I think, obvious, right? So we want to have a way, as soon as we bring those environments into immersive and photorealistic representations, we also want to interact with those spaces. And that requires that we have a form of disentangling the scenes into the individual objects. So what's the main challenge here? So with panoptic lifting, when we depend on 2D inputs, what we get from 2D segmentation algorithms is obviously a lack of consistency across the frames. So not only the masks might vary a little bit, but also the class assignments might change over time. And this is particularly like difficult to solve for the object instances because there's no notion of like an object ID that we can, stably track over time. And another thing was, is there a chance that we can get rid of 3D bounding box supervision? Because whenever you depend on an additional form of input, obviously it's challenging to make sure that also this input is robust enough so that you can depend on it. So what we did here was essentially, and this is the basic training pipeline, we have been building this neural field representation, again, as a form of comprising color, of density, of semantics, and of the instances. And in this form, we used a tensor F representation for the representation. And then we also essentially added the way to like nicely disentangle the instances in the form of surrogate IDs that we're able to decompose as part of the training process and identify the IDs that allow us to keep a stable track of the individual objects over time and as part of the 3D representation. So once this project was, so we've also kept like evolving on this project, where essentially we started integrating additional information by further refinement in terms of the 2D inputs. So we've been leveraging grounding dino and also the segmentation algorithm from that was published as Segment Anything, which is agnostic about the classes itself, but together with grounding dino, it still allows us to have a much more fine-grained representation, the fine-grained decomposition of those things. Good. So nerves are cool, but Gaussian splatting is cooler. So what we looked at was we needed a much more like sophisticated way and a more efficient way to represent the scenes because training should be faster. And frankly, also inference is, of course, very important because at some point we want to render those representations with super high frame rate and at high fidelity. So what we started to look at was the Gaussian splatting formulation, like I think many other people did. And what we found was that if you follow essentially the basic like training pipeline, that once you have taken care of the actual parameter learning process for the Gaussians, you also know that there's a form of like density control mechanism that's part of the Gaussian kind of learning procedure. And the main problem that we've identified here is that this, in our opinion, wasn't done in a really principled way. So instead of using or leveraging the like official or original form of adaptive density control, we started looking into like finding a more optimal and more principled like form of like controlling this density procedure or density mechanism. Let me like quickly recap. So the standard density control mechanism from Gaussian splatting essentially leverages accumulated positional gradients of the existing primitives. And that comes with a couple of like disadvantages. And so what we typically see is that in very highly textured environments or highly textured regions, the positional gradient doesn't really change over the course of like an update cycle. So which, very often leads them to these very kind of blurred out areas that you can see here in the grass area, which is one of these high textured areas. The other thing is the different type of like pruning or growing strategies, they are like very much driven based on heuristics, and finding the right like hyperparameters or thresholds is very unintuitive. And in the worst case, you would have to like calibrate this for every single sequence or every single form of like capture that you do in reconstruction individually. That obviously is not something that we want. And the last thing, there's no like obvious control mechanism for integrating like a ceiling or an absolute number of Gaussians that you want to like incorporate. And this is also something that we've been addressing. So what we're essentially doing is we are proposing an additional auxiliary like per pixel error function. And this helps us to like really trace back or track back the information in terms of the gradient with respect to every single Gaussian primitive. And if we do so, we actually have a much better way of like assigning gradient information proportionally to each Gaussian, and then ultimately end up with something that also allows us to overcome those issues in those highly textured kind of areas that I've shown before. And what you see here is like, as opposed to like the standard way, you can also manage to get these nice high frequency patterns reconstructed well in this ViLMa 360 dataset. So I'm not going to play the full video again here, but essentially this reconstruction was already leveraging this form of new or alternative densification mechanism. And this is also what allows us to really have a fantastic kind of reconstruction results in those repetitive and highly textured areas. Good. So, given that we've made quite some advances on the reconstruction problem alone, can we say we're done? Have we succeeded yet? And I think that's a clear no. Not only because we want to all keep our jobs and keep working and have like great research experiences by moving the needle at least a little bit. There's also this other problem that we haven't really been talking about too much. If you want to do a high quality reconstruction from nerves or Gaussian splatting, you need a lot of images, and it's really painful. If you think as a user, you are capturing your environment and you have to take, let's say, 600 or 1,000 images, people will not do that now. I mean, I wouldn't do it. But this really is the reality. So if you're talking about this like as a pure reconstruction problem, what you typically have to do is like run around at different height levels, at different areas, have different kind of like angular representations of the environments to really get a crisp and nice looking reconstruction in the end. So if we are in this like bar where we'd say we treat this only as a reconstruction problem, then we are at the very far left here, as opposed to some form of generated reconstruction result or synthetic reconstruction result, which would be on the other side of the spectrum. So what we started looking at also last year was a project together with some of our university collaborators in Munich, which is called GANNERF. And here really the goal is to leverage from imperfect input data, trying to see if we can do better in terms of reconstructing high fidelity reconstruction results in areas where we don't have a ton of observations. So here we're using a form of adversarial formulation where we build up additional gradient flow in the model so that we have a much better and more 3D consistent form of representing this in the radiance field, and also add some additional terms that I'm going to show where we can do additional upcycling or quality upcycling of the final outputs. So I think I'm already close to time, so I'm going to speed up a little bit. Oh, okay. So it's fine. So again, the really nice part about this, all of a sudden we can handle insufficient areas or areas with insufficient observations, where we have potentially blurred input images, where we potentially just have suboptimal input data, which is a real thing to handle. And so we built up this architecture here, which, so in addition to the post-input images, we're also looking at essentially leveraging this multi-view RGB inputs and then do patch sampling from the input images, right? So what we would want is some form of adversarial setting in our model that helps us to understand, hey, is the 3D or is the 2D image that I'm rendering from my radiance field, are the underlying kind of patch statistics and the characteristics that we're observing, do they match the observations that we have from the training data? And this is a really nice kind of way to leverage this GAN kind of formulation, because all of a sudden we have this feedback that we can incorporate as gradient information back to make the model essentially more robust to those issues. Yeah. So this is done by the first discriminator. But we also have a conditional generator involved, which essentially consists of this feature extraction pyramid, where you have different blocks operating at multiple resolutions. And then essentially the goal is to like gradually start from downsampled patches and then have convolutional blocks that allow us to do level-specific features that are then upsampled and gradually kind of combined into the final kind of higher resolution output that we want. This is inspired by StyleGAN 2 architecture, but we essentially introduced this conditional functionality and removed the mapping network. So we've also done a couple of experimental evaluations. And one of them that I find really interesting and particularly kind of encouraging is that in a setting where we started to gradually reduce the number of images, so from 800 down all the way to about 25, it's a little bit sparse. But that we show that we can really retain quite high quality and high performance on the reconstruction result, even though we like significantly reduce the number of input images. All right, there's a ton of more papers that I'm not going to cover in detail, but that we also present. There's two here, and there's another one that I don't have here, but that we also present at CVPR. One of them is essentially moving again, if you think of this virtual slider, moving more into this synthetic or generated spectrum, where we have a way to also do high fidelity stylization and do that in a 3D consistent manner. So this is something that we're presenting in poster session 5. So please come and take a look. And then there's another paper that we call multi-div. Where essentially the goal is, given only a single input image, can we generate an entire kind of room or an area around that image that is fully consistent with respect to the input, and then do a view extrapolation by just providing the target kind of camera trajectory, and then let the model infer the remaining part. So this is then basically at the very far right of the spectrum that I showed before. This is basically almost fully synthetic generation of scenes alone. So for both of the papers that we present, we have state of the art right now, and I'm really encouraging you to go there and take a look at the posters. Good. That's the end of my talk. My summary would be, I think we really want to be able to generate methods and architectures and algorithms that allow anyone to produce high quality, high fidelity reconstruction results so that we can populate the metaverse in the way that we want it to be populated. We have to make this super easy, super simple, and super robust with respect to all types of input data that we are able to capture and that people will actually capture. There's ML-based semantic representations that today lead to photorealistic 3D representations or contribute to these type of representations. And they're awesome. But again, I think we have to make them more robust, and there's still a ton of open challenges that we should address in the domain. And finally, and we only briefly touched this in this presentation here, but the generative models, they are also here to stay. And I think there's going to be a very strongly intertwined kind of form of pulling reconstruction together with generation together, so that we get the best possible outcome in terms of fidelity and in terms of completion, in terms of stylization, and in terms of pure synthesis, of purely synthesized environment. Sorry. Okay, and with that, I'll leave you. My team is hiring. If you're interested in a position, junior and senior level, more senior levels, please reach out to me directly. Thank you.
Are there any questions from the audience? Please go to
So thank you for the feedback. So I see that you mentioned that the nerve and thought setting are very specific to very accurate photos. But I think probably because the kind of complexity and that's related to this issue. And I think ever since Spark comes out and people, the default way of approaching this is they currently optimize code and then okay, work, but actually in our practical experience, it doesn't work so that well. And there are many cases that are far away outliers that just can't be correctly. So I would like to ask for your view, like how can we possibly fix this problem? And because of the transformation, very costly, time consuming, and may not be accurate. So what are your thoughts?
Yeah, so this matches actually pretty well with our observations as well. So we cannot recover from arbitrarily bad post information. So this is something that we tried for a while, but there really wasn't a good chance to solve this problem or address this task. We have another paper that we've also put on archive recently where we addressed, it's called robust Gaussian splitting. Well, thank you for hopefully citing it later. I think what we tried to find there was a better integrated form of doing post refinement together with the Gaussian primitive formulation. I think that was a very natural form of like combining these directions, and for the Gaussians, it turned out to work pretty well. We have had more challenges when we started looking into like the more or into those earlier solutions like BARF that we mentioned as well. It also didn't really work for us. For the joint static and dynamic representation that I showed before, we actually have an additional post refinement procedure that leverages the entire scene graph formulation, which is something that helped us to make things more stable and robust, because all of a sudden we turn away from only optimizing the poses on a per image basis, but really try to like jointly optimize this for the entire graph. So maybe that's one direction to look into.
Thank you.
Any other questions from the audience? Or you have the time to ask them. Is there any more questions? So then I would like to thank the speaker again for the great talk, and we can continue this. Thank you.
I think you need to take the sound from there, but can you press on that next to the go to audio settings, because this one, and then there's it like automatically adjust. Can you turn this please off and put this to the loudest, because people were complaining that the voice is silent. I think that should work. Yeah, I think that's good. Okay. And I think you can just share the screen, and then you can use that mic. Okay. Sometimes it's randomly going off, and we just need to check and wait a second, and then it suddenly works again.
Okay, just let me know. Okay.
Right, so let me introduce our next speaker, which is Laura Latouche. She is a senior research manager at NVIDIA, as well as an adjunct professor at Technical University of Munich, where she is leading the Dynamic Vision and Learning Group. Before that, Laura received her PhD from Leibniz University of Hanover, and she spent time as a postdoc at ETH Zurich as well as at TUM. So Laura, we're looking forward to your talk.
Yeah, thank you for the introduction. So yeah, today I'm going to talk a little bit about exploring different scene representations for visual localization. So I don't think I need to explain to anyone what visual localization is, but let's ease into it. So let's say that I'm in, this big scene, and I want to know exactly what I'm looking at. So I want to essentially take a picture, and I want my localization system to tell me exactly what is the orientation and the position of the camera. And this has to be done in a very accurate way, something like centimeter or millimeter accuracy. So now a localization system has this query image as input. It has also a scene map representation that classically has been either, a set of reference images that you have collected before, or a 3D point cloud that you have reconstructed with something like ViLMa. Then you have, your favorite method to obtain the camera pose as output. And as far as methods go, there's a tons of research that is happening on several paradigms of localization: absolute pose regression, scene coordinate regression. There's also image retrieval or relative pose base, which uses the references images as input. And then there's the more classic, more studied structure-based methods, which actually use the 3D point clouds as input. And, there's some learning involved here and there. Some methods are end-to-end, some methods have learning sprinkled here and there. But they all use these representations of either, the reference images or the 3D point clouds. And the question of this talk is, how can we change a little bit these paradigms? For several reasons. Can we actually use more advanced representations or simply different representations? And how would we go about doing visual localization on those new representations? So let me start by a brief overview of structure-based localization. So we have our 2D query image, and we have our 3D point map. And essentially what is happening in most structure-based methods is we obtain a set of key points in 2D, we obtain a set of key points in 3D, and then we want to do matching between 2D and 3D. And for this, we use a series of descriptors, both on the 2D side and on the 3D side. You launch this into a matcher and then put these matches into a PNP solver. Now, this is really nice, but it comes with 3 practical challenges. The first one is maybe obviously storage, right? So to store these key points, it's actually really expensive. And especially as the scene grows, this becomes more and more expensive. So for example, like for storing super point for mega depth, it requires 1 terabyte. So that's one challenging thing that doesn't allow us to really scale up to huge scenes. There's been work, of course, on like scene compression, quantization. So people are looking into actually reducing the memory footprint. Then there's a privacy risk, right? So there have been recent works that have looked into descriptor inversion. So going from these visual descriptors all the way to the original image, which could pose a privacy problem. And there's people working on actually privacy preserving descriptors and reducing a little bit the risk there. And then the third one is the maintenance complexity, right? So we keep coming up with new visual descriptors, right? I mean, there was SIFT and then, cap, superpoint, et cetera. And this means that every time that we want to perform localization with the newest, best descriptor, we're going to have to change the map. We're going to have to change the whole system across devices so that one can do the localization. So this is, of course, you have to rebuild maps, you have to upgrade scene descriptors, it comes at a cost. And again, here people are looking at ways to leverage the previous descriptors and not have to do this maintenance all the time. So for us, what we say is, okay, how about we tackle these challenges head on, right? Like storage, privacy, and maintenance by essentially bypassing the visual descriptors, right? Like, can I actually perform 2D, 3D matching with only geometric information, right? And this is the first type of representation that I'm going to talk about. It's still a point cloud representation, but now we're kind of throwing away all the descriptors which make the match task easy, and we want to directly use only geometry information for matching. The good thing is that it's going to require lower storage. It's going to be naturally privacy preserving, and there's not going to be this descriptor maintenance, right? So potentially we can tackle all 3 challenges at once. So we start from a work that was called BPMPNet, right? It was learning-based, and this is kind of the first work that proposed this geometric-based matching. But it has a big problem, and that is that the performance really degrades when you start adding outliers to your scene. So here we can see 3 plots based on accuracy at 1 pixel, 5 pixels, and 10 pixels. And you can see the accuracy of BPMPNet, which is the gray line, that starts to degrade really, really quickly all the way to something that is not really usable already at just 50% of outliers. And unfortunately, this is what real-world localization settings are, right? I mean, these are the types of outlier rates that we need to deal with. So our question was, can we actually bring something like BPMPNet? How can we bring it to an accuracy that is usable for real-world systems? So we start with their type of architecture, right? We start with that kind of error there on the top right. And the question is going to be, what kind of ingredients can we use to bring this error all the way from the top right to the bottom left? And so just roughly speaking, we have such an architecture. We have the 2D key points from the query image that we're going to extract some features with the network. We have the 3D key points, again, another network for extracting features. And then we're going to have a matching layer, a synchron layer that is going to learn the matches that are going to be passed to the pose solver. So the first thing that we observe and the first thing that we're going to change is actually the representation, right? So you're asking your network to match two things that don't really live in the same space, right? I mean, on the one hand, you have something on a pixel space. On the other hand, you have just, 3D positions. And these are really hard to match, right? So the first thing that we're going to do is we're going to change the representation of the 3D points, and we're going to use a bearing vector representation, right? And a bearing vector represents the direction from a reference camera origin to the 3D point. So now you can see how we have changed from just, 3D points and providing some locations there to a representation that is much closer to the pixel space. Of course, we need to have these reference views, but this we have anyway, because image retrieval is usually the first step in localization systems. So this is something that we're still going to be using in our system, in our Go match. And you can see here that already we go into the right direction of reducing translation and rotation error. The second key change is we're going to use a shared encoder, right? Like now that we have two elements that are both in 2D, we can actually use a shared encoder to extract some features from the 2D key points of the query and the 2D key points of the retrieved images. And this is going to improve, again, accuracy a little bit more. Now, the biggest boost in accuracy is maybe unsurprisingly from some attention layers, self and cross attention layers. They're going to basically make the task of the matcher much easier, right? So the two types of features have already talked to each other. They already know, if they are similar or not. And now the matching task is much easier. And finally, we're going to have a very simple outlier rejection step that is going to remove, further outliers. Now, the last thing that we can do is, since we're not going to use directly 3D key points, but we're going to use the bearing vector representation, this changes with every image that you use as your reference camera. And so what we can do is actually, we can take simply more co-visible views that are coming from image retrieval and just represent all of them with bearing vectors. And this improves the accuracy further. So with all of these ingredients, basically, we were able to bring the error all the way from the top right to the bottom left, making essentially the system usable for real-world cases of localization. So let's see some experiments that are interesting, right? So the first one is, what kind of generalization does our method have, right? It's a learning-based method, which means that it might as well overfit to the scenes that you train it for. And this is something that we want to actively avoid. So the first thing that we try is, does it generalize given the type of key points that you train it with? And so what we do is we train our method with sieved key points, and then we test it with superpoint. Now, remember that we're throwing away the visual descriptors, right? So we're only keeping the position. And this actually allows us to really generalize from one descriptor to another. So we don't have any problem of maintenance anymore. And the other generalization aspect that we want to observe is whether we just train the method on indoor and it can generalize, for example, to outdoor. Now, it is a rather extreme setting And the results are, of course, not state-of-the-art, but this allows us to test the theory that actually there's good generalization, even from indoor to outdoor. Now, just a bit of comparison with state-of-the-art on Cambridge landmarks. We compare geometric matches, which are the yellow ones, with end-to-end learning methods, which are the red ones. And finally, the classic structure-based methods, which are the blue ones, which are traditionally the most accurate ones. And just here to highlight that with GoMatch, we were able to bring the essentially the inaccuracy of geometric-based methods all the way from up there, this was the BPMP net, to something that is actually on par with state-of-the-art and is actually usable in real-world settings. And when we talk about storage, of course, like geometric matchers have a really, really low storage footprint. Okay, so this was kind of the first type of representation that I wanted to cover, which was the descriptors-free point cloud, plus the reference images that we're always going to use for retrieval. And we show that GoMatch is actually a valid alternative that is on par with state-of-the-art. So this is something that now we can use, and we can think about doing research on top of that to further improve accuracy. But you know, is there an even more compact, and I would say not only compact, but even useful scene representation, right? So we turn quickly our look into NeRFs, which are not only more compact and more interpretable, but they also have the ability to generate images, right? From different viewpoints with different characteristics. So it does so much more than just represent a map and represent a scene, right? And our question was, can we actually create a method that, without touching a pre-trained NeRF, uses NeRF as the primary representation for visual localization? And NeRF was, of course, not really trained for that, right? And the question is, does it have the features internally necessary to do visual localization? So that is our main question. So we start with our query image and our NeRF, and the only thing that we're going to store from the training process of the NeRF is going to be the training poses, right? We're not going to store anything else. We don't want to get access to the original images because we can actually generate those images, right? We can use NeRF to generate our synthetic database with the training poses. So it's like we have access to the original images. And one might say, well, but then you need to store the synthetic database anyway, right? So you have the storage problem. It's true, but you can do this in a smart way, right? I mean, you can do this by different parts of the scene. So splitting the scene in different parts and then doing a hierarchical generation. So there are ways to even reduce further the footprint of saving that database, even though that's not the biggest problem here. Now we're going to use that database again to perform image retrieval and obtain a series of reference poses from the training images that are closer to the query image. So this step remains untouched, but we use the synthetic images generated from NeRF. Then we're going to have our NeRF representation, right? Series of layers generating the color and anything else that we want to generate. And again, we don't want to really touch that part, right? We don't want to really retrain it. We don't want to generate external features. We just want to know which are the features that would be best for visual localizations. The one closer to the point representation, to the input of the NeRF, or the one closer to the color when you're actually, generating the color. So we're going to use these NeRF features at different layers. And we're going to use the 3D surface points, again, generated by the NeRF. And on the other side, we have our query image that we process with your favorite 2D encoder and obtain the image features. And now, essentially, what we put on top is a matching layer that is going to match the 2D information coming from the query image with the NeRF information. Okay, so let's move then. Oh, yeah, and this goes to PMP solver. I mean, this is all the same as previous localization methods. So let's go into experiments. Let's see, what works and what doesn't. Essentially, that is the main question here. Like one of the questions was that, oh, okay. So I wait now?
Yes.
Okay.
I think the only way is to wait.
Oh, a classic restart. Love it. Okay.
It happens all the time. It happens all the time. It should come.
should come back after some time. It happened like 3 or 4 times already. Yeah, now it's back.
Yep. Okay, cool. So yeah, one of the questions was, does NERF, do these NERF features that were not trained at all for matching, that were not trained for localization, do they contain the necessary information to perform 2D, 3D matching, right? And it turns out that they do. And it also matters which layer of the NERF you're going to use, right? And it turns out that if you take, somewhat a layer in the middle between the point 3D representation and the actual color generation, the middle is where it's best to perform the visual localization task. And not surprisingly, if we get closer and closer towards the end, the error just boosts up because, of course, the features are more targeted into color generation, density, and so on. Now here we do a comparison with other ways of using NERF, right? I mean, we were not the first ones of thinking, let's use NERF for localization, right? So there's the blue methods, which are using NERF basically to augment the training images, right? I mean, this capability of generating images from new viewpoints can be used at train time. There is the purple one that uses test time refinements with NERF. And then there's the red methods, which are closer to what we're working on. And this is basically training a NERF and a matcher together. Now, these, like some methods require depth and image inputs, and this is something we want to avoid, right? We don't want to retrain the NERF, that's one thing. And we also don't want to require extra inputs. So these are the differences with respect to the red methods. And we can see that, again, there, we are on par in terms of centimeter translation error and rotation error. Then the final comparison is with feature matching with classic structure-based methods, and there we are on par with HLOC on Cambridge landmarks. And I have to say that this is quite a challenging environment for NERF training, so we had to put some effort to get a proper NERF representation. So there are some details in the paper that you can check, but I think it's also quite cool that you can actually do localization and be so accurate with a NERF representation. So without something that has been specifically trained for the task of 2D, 3D matching. Now, things that don't work. Indoor accuracy is not so great. So you can see here 3 blocks of methods. The first one is absolute post-regression methods. Then we have methods that actually use also 3D. And here in the end, we have the NERF-based method. And you can see, especially if you look at the last column, right? If you look at recall, we're really like 20 points behind in recall. And so we ask ourselves the question, why is that? Why is this working so well on outdoor scenarios and suddenly indoor it doesn't work? Now, it turns out that, first of all, there are some depth inaccuracies, right? So we are actually using NERF predicted depth maps. And any kind of incorrect depth prediction is going to lead to wrong feature correspondences. And in a small scenario, such as indoor cases, this leads to a huge error. Now, other methods like image matching or SCR, APR methods, they all use directly camera poses and 3D maps that are accurate. And we never use directly this supervision. The other thing is that we're not yet really good at filtering inaccurate matches, right? So this whole like outlier rejection, filtering matches is something that the method is not really good at doing. And this has a very large effect on small scenes, of course. But on the bright side, we scale much, much better to outdoor scenes compared to regression-based methods, right? So there is here the potential to scale up to really large scenes and really make use of this compact representation. Okay, so yeah, I'm going to basically conclude my talk here. I've talked about 2 potential new representations, scene representations that one can use for visual localization. One is essentially taking a descriptor-free 3D point cloud, and we actually show that geometric localization is possible and is somehow up there with state-of-the-art. And it actually bypasses storage problems, privacy problems, and descriptor maintenance problems. And the second one is essentially like, I would say, an initial step towards using NeRF as the primary representation for visual localization. Super compact representation, interpretable, actually able, like the features themselves are usable for 2D, 3D matching. And of course, you know, you can use NeRF for your favorite image generation and still use it for visual localization. So I think that's pretty cool. Okay, so with that, I will conclude my talk. If you have any questions.
Yeah, please go in front of the microphone to ask your question. Thank you.
Thank you for your presentation, but I still want to ask, what's your NeRF matches advantage compared to the same coordinate regression method like ACE and GLASS?
Mm-hmm.
Yeah. Because they also can get the 3D correspondences directly.
Yeah.
Yeah.
So I actually had a slide about this. It takes a little bit of discussion. So first of all, we are more accurate. Yeah, you know, that's always a good thing. So here I'm comparing with these kind of methods, right? And it's like our method is very similar to SCR because, you know, they match, they map RGB to 3D points. But I would say that we don't first of all, we don't really need the original images and, you know, train our matching on top of the original images, right? So I can just give you the NeRF, which is the compact representation, and then I'm going to do localization there, right? So that's a good thing. We like the paradigm is slightly different, right? Like we do matching, they do regression. We also try to do regression with like a regression paradigm with NeRF. Yeah, it doesn't work so great. But I would say the representation is the main advantage, right?
Give me some data about the training path and the throughput inference.
The training, sorry, what?
The training path and the throughput when inference.
Yeah. The training, honestly, I don't know. It doesn't take forever. Like I've definitely there's projects that definitely take more GPU time. That's for sure. Yeah.
So
I mean, you're just training the matcher, right? I mean.
Yeah, I mean, for example, for the inference, give you a query and compare to ACE, or what's your inference on the runtime for give the output, the 6 output?
It's on the paper for sure.
Oh.
We can sync later and we can look through that. Yeah.
Thanks.
Yeah.
Hi, Dr. Gaurav. Thanks for the talk. So my next question, I think it's kind of brilliant that you found that, you know, something that is, you know, trained to be appearance dependent actually have some of this invariant learning, which is kind of required for localization.
Mm-hmm.
So my question, I think I had two mini questions. One, why do you think that is the case? Why, you know, learning is delayed? And the second is, does it make, I mean, is there a way where we could use a different representation instead of say RGB and use some other feature map, say, I mean, Dino or something that you can train, but and would that lead to better localization output?
Yeah. So with respect to the first question, like I said before, I just hinted to it that training NeRFs on Cambridge landmarks is a little bit painful. And one of the things that really worked is to use these appearance codes. Like, for example, for a grade code, there's like crazy illumination changes. And if you actually use this appearance code, then the NeRF has a more invariant representation of the scene, right? So that's quite crucial for this. Or like, for example, handling dynamic objects, right? You can use your favorite segmentation method to basically ignore those areas. And this is also really important. So how you train the NeRF is going to really give you completely different representations than for matching, right? So that's one thing. And I forgot the second question, sorry.
Yeah. But using other features instead of just that.
Oh, so this we didn't try, right? We just wanted to get, you know, your classic NeRF, right? Without being augmented with any features that, of course, like would require more storage, right? So this was really like your basic nerve, and it's kind of an initial step, I would say, to study, okay, is this even feasible, right? And now you can start throwing in more features, for sure. Yeah. Yeah, sure.
Hi. So the trained nerve usually you do like this. Sometimes the artery runs feature matching and then you train, and then you go to nerves and then you do matching again. So it just seems kind of like a chicken and egg problem where maybe there's already some errors in original matching that kind of pertains to nerves and that keeps going. So I guess what would you say to that?
I mean, we're also using ground truth for localization that is coming often from these reconstructions, right? So that's also not great. So there's already an element of error there, and there's been tons of papers, like Thorsten has worked on that, has like probably wonderful insights. Like the thing is that we don't really want to use the original images, right? Like we don't want to depend on that first matching step. And of course, the errors are going to trickle down to nerve, right? But some of those errors are corrected because nerve is basically, is not trained for matching, right? It's trained for something else that corrects a little bit of those errors, right? A little bit, like that's like, take it with a grain of salt. And this thing that we don't want to use the original images means that we cannot really, rely on that matching, right? Like we don't want to go back to those images and then, this requires storage and so on. We just want to take the tiny nerve, give it to you, and then you're able to do localization. So I think this is the main constraint for not using all that prior information.
So, okay. Thanks for a nice talk. I had a question on the descriptor free key points. So basically, you're going back 25 years in time, pre-introduction of descriptors, and it was a huge boost, right, in performance when we added descriptors. And now you take the descriptors away, and it still has the same performance. What's your intuition for that?
Oh, it's all learning, right? I mean, you showed the attention layers, everything. Yeah, it's all learning. Like basically, all the information that you put into descriptors, you now basically put into learning patterns from data, learning a pattern of, I don't know, this is, the head of a church, and this is what it looks like in an image, and this should be matched, right? So it's all like your, classic data hungry method. There's no secret sauce there. Yeah.
Pretty cool. And what about computation?
For the geometric matching, it's much cheaper, right? I mean, this is just like a forward pass, and there you go. Again, it's in the paper. I should really memorize these numbers, but it is in the paper, I promise. Yeah.
So maybe test these in other data sets. Like I think one potential problem is if the descriptors, if you're not using descriptors, if you have too many potential key points, it may be more difficult to match them, for example. Maybe is there anything that's more specific to this data set that you may be leveraging?
Oh, no. We have tons of data sets in the paper. I didn't want to go through all the results, but there are more data sets in the paper. We didn't observe something that would be pathological in the method, right? Of a given data set, like, I don't know, illumination changes or something like that. So it's actually pretty robust, I would say. Yeah. And the good thing is that it's going to scale up with data, right? So the more data you give it, the more it's going to be robust, et cetera, et cetera. So yeah. Yeah.
Any other questions from the audience? Seems not to be the case. So I would like to thank the speaker again.
at Carnegie Mellon University, and his research mainly focuses on enabling autonomy in challenging environments. He and his team have shown several fits for the autonomy of flying robots and off-road driving. Professor Scherer received his Bachelor in Computer Science, Master's and PhD in Robotics from CMU in 2004, 7, and 10. It's a great pleasure to have him here today. Sebastian, you can go ahead.
Thanks, thanks for the introduction. And so today's talk, I want to kind of maybe shift. If you want to have one takeaway message from today's talk, is maybe that there's a big range of environments that you want to use a lot of these vision mapping, localization algorithms in, that they are not initially developed and evaluated for. So maybe looking at these other domains can also be valuable, right? It's not that's not where the bell curve of value is. It's like indoor driving, VR, AR, right? That's where a lot of work is going on. We're at the tail end, but that tail end has a lot of interesting challenges and is still very relevant. So what we are interested in is how can we have estimation and mapping for these safety critical and situations where we still want to have high accuracy, and we want to close the loop around the output from these algorithms. So you see things like the left is here sub-T challenge, off-road driving, flying in wildfire in these challenging situations. Also, if you look behind us, there's actually a lot of challenges here. If you wanted to operate autonomously between those skyscrapers with a vision-based system, it's been actually very distracting for me. And it's office space if you want to start a company. So here, just to give you some motivation, this is from some of our sub-T challenge work. You can see here there's some dust, it's dark. There's lots of autonomy challenges, but if you just think about the state estimation and mapping pieces, right, you have lots of challenges here if you want to use something that uses cameras, or even if you use other sensor modalities. And so in the end, what we want is we want an agent that is semantically aware of the environment. We want to have this kind of unified inference and combine that together. But if you look at really the key challenges to have robust perception for a lot of, and there's different ways you can try to handle that where you don't rely on robust SLAM as the key part. But if you want to think about that as the key part, that's one of the things. Typically, if you look at a lot of research, the focus is on accuracy and efficiency, and that's part of that is because it's much easier to measure. And I'll come back to that at the end. So, as any researcher, we want to go in and have some good baselines and data sets to work on. So one of the things we recently did is release a data set that tries to really tease out these challenges. So it's a combination of some of the purposefully collected data, some of the data from the sub-T challenge, combined with the Tartan Air data set, which is a simulated data set where you have good ground truth, but also lots of challenges. And in ICCV 23, though, we had a SLAM challenge, and there's still no solution, so it's still kind of a valuable data set to look at. And so how can we achieve robustness for SLAM? So once we have these data sets, or we want to do this in real time and close the loop, one of the ways we've been looking at this problem is to try and combine different sensor modalities, really kind of trying to center around IMU. So here we have LiDAR odometry, then we go into a smoke-filled room where we lose visual and thermal. So now visual and LiDAR, now we're looking at thermal as the prime modality to do state estimation. Once we get back out, we switch back to LiDAR. Then we get to a situation where LiDAR is ill-conditioned because it's a very narrow corridor, and now we're mainly relying on visual odometry. And so how do we do, and the key here is really to figure out what modalities to trust and which parts of the odometry estimate to trust in which situation. So you can kind of see some of the environments that we are looking at to try and operate in. Here's a similar problem, this time on a drone, where we're looking at visual and thermal. So this drone is too small to carry LiDAR, and so you can see this is at night. We're setting off some smoke bombs here, and so you can see how the visual gets occluded by the smoke, and then we're tracking with the thermal odometry. But the accuracy of the thermal feature estimates, for example, here is not as good as visual feature estimates if you can actually see something. So there's this big trade-off. Similar for off-road driving, one of the challenges we have is how do we get dense and long-range depth estimates, and we have pretty high accuracy requirements, right? Much higher than autonomous driving, because you have to make much finer grained decisions, right? For autonomous driving, you're just looking for relatively big objects. Here we're looking at, okay, can we distinguish between small rocks, fine rocks, grass, a lot more subtle decision making. And so here we've been looking at, can we use a develop a learning-based method? Now, a vulnerability of all of these methods is you have to look outside, right? You have to see LiDAR, you have to see thermal, some other features. And so can we really look at IMU-based measurements to try and make the system more robust, right? So super odometry relies on IMU a lot, but can we reduce drift of and so IMU really drives your lower bound in terms of how robust your system. Any kind of modern, step back, right? I mean, any modern system today has an IMU in it, right? Like your phone has probably more than one. Your cameras, sensors, everything has an IMU built in. So one of the question is, can we really maximize how much information we can get out of the IMU to increase the robustness of SLAM estimates? And so many of the other sensors can fail with degradation, but your IMU will hopefully not. It also gives you a way to have a high frequency estimate, right? Because you can sample these measurements very quickly. And so there's a couple of problems with IMUs, right? Otherwise, we would just be using IMUs. So one of them is drift due to noise, and the other one is characterizing uncertainty. And so for uncertainty, there's some first principle methods, but what typically happens in practice is you start out with good intentions, do the first principle calculation, and then you hand tweak the covariances until your estimate is good. Right. So there's a question about characterizing this uncertainty. And so traditionally, when you use IMUs in a SLAM system, you integrate the IMU, you have your hand-tuned or identified uncertainty covariance parameters. You set up a pose graph, and then you integrate this with the rest of your system. There are some other methods that try to directly predict velocities or delta positions. The method we look at here is to try and instead predict delta biases for the integration for both IMU accelerometers and angular rates, as well as predict the uncertainty that maximizes the position. And the key here is that we differentiate through the pose graph optimization to then do this, to then learn the network. So here's that we go through these blocks to learn that network. And so that's kind of an interesting piece. Yeah. So we designed a network to do this, and then develop a loss that captures balance of error and covariance with some regularization so that this does not become ill-conditioned. And then we can learn this model. So one of the things we don't know yet is if it, nominally what we just claim is that if you learn on one particular IMU, it should improve that IMU's result. There's a question if that generalizes across classes is a little unclear. So we tested this on 5 different data sets, one with some low-cost IMUs all the way to navigation grade or high-end tactical grade IMUs. And so on the low-cost IMUs, we can get a better estimate of the get better estimates compared to caliber. For other methods, we can get a 40% reduction in RMSE. On Kitty, we can get a smaller velocity error, and that velocity estimate is stable. And then here's an example from the sub-T MRS data set that I mentioned earlier, is that when this robot is sitting stationary, the velocity drift area is much less. And here's a result for integrating navigation grade IMU. So so here we have a run that is so we use, let's say, trajectory B is the training trajectory. And so we use that data to learn the network. And trajectory A is a test trajectory. So this is IMU integration only. There's no outside references. And so we are able to reduce the endpoint error by a factor of 2 to 4. And so the idea is really that what this allows you to do is this network gives you more parameters to capture some of these errors that these IMUs have beyond a standard calibration where you only have 3 numbers or 6 numbers. Now, the other part of this is the uncertainty estimate. So if you have, if the other thing that turns out is that the uncertainty of the IMU measurements is not stationary. So typically, as we assume in these postgraph optimizations. And so here's one result from 2 sequences where we either use the learned covariance or we don't use the learned covariance. And you can see here that with the learned covariance and our model, you get the best results, but even just using the learned covariance still gives you a better output. So just to kind of summarize, so across kind of wide range of data sets, we get some improvements in terms of the performance of integration itself, as well as the uncertainty estimates. And so this serves, this AIMU model serves the purpose of identifying noise, reducing some of the noise, as well as estimating a better uncertainty. And this better uncertainty helps you with the postgraph optimization. And on the high level, the key idea is that by being able to differentiate through this postgraph network, now you can learn this model using a library called PyPost that has been developed by one of my former postdocs and some people in the lab. So you can, in that library is an extension to PyTorch where you can add some of the more traditional methods such as integration with learning-based methods. Now, once we have a system that can do robust odometry for us, the next thing we of course want to do is ground that odometry in the real world. And so for that, we've with a team of collaborators developed this method called AnyLog that tries to really push where you can do this place recognition. And you have lots of introductions before. I'm not going to go over this. Here we're really looking more at, let's say, the image retrieval piece of this. Like, how do we know where we are? And so we want this method to work anywhere, indoor, outdoor, overhead views, underwater, all kinds of methods, places. And then, with different lighting from day to night, and then different viewpoints, like fisheye versus top-down, indoor, and so on. And so one of the key motivations was that these place recognition methods have worked well in many urban situations. There's especially people really love to use Kitty, for example, or these areas, but it's just a very limited environment, right? Like especially all self-driving data sets have a very limited viewpoint that does not really tell you much about generalization. But so when we try to use these methods in a more general context, they don't work well. So what we looked at is, could we use foundation models to try and get a more generalizable place recognition system? But then if you just use them as is, they actually don't perform very well. Basically use one feature per image. So instead, what we looked at is to extract a layer out of Dino V2 that was very informative and had a good contrast, and then on this per pixel layer to use different aggregation techniques to get a descriptor. And then we put together a test bed of 9 different data sets and tested this. So here you can see one data set that we call Hawkins. And so you can see the best retrieval is the star. So the closer that star is to the green, the closer you are to the ground truth. So this is the top score. It's the same method in a top-down localization task where trying to match to aerial images. And then, so there's some details that I skipped over that you should look at in the paper in terms of how you actually try and construct this ViLab descriptor. But high-level idea is that there's a lot of informative information in these middle to final end features in Dino V2, and then with some aggregation techniques, you can get very good place recognition performance. So this kind of gives us a good way to do this state estimation over the longer run. And so for many other use cases, especially when you think about flying drones, we can't afford to carry LiDAR scanners. So we look at, want to get a depth estimate. But the challenge with regular stereo cameras is that they have a very narrow field of view, right? For a drone, we want to be able to fly in any direction. And so it's up, down, left, right. And so what we looked at is fisheye-based depth estimation. And so this omnidirectional depth is very important to us. And so, but it comes with some complexity. There's not a lot of work on this fisheye, and fisheye images are also therefore a little more painful to work with. So, so there's a couple of challenges with fisheye images in terms of the resolution, right? So it's an uneven resolution as you go across the field of view. They're a little harder to simulate, and so on. So when you think about regular stereo, you have 2 images and you're trying to match across the epipolar line. For fisheye, now you have a spherical view and you're trying to match. Oh, cycle. Yeah. Test. Oh my God. Okay. So timer is up. Next candidate's turn. Okay, so for the epipolar, so instead of epipolar lines, now you have epipolar curves, and so you have several spherical candidates. So you have several spheres that you're trying to match across. And so what you typically try to construct is a cost volume, right? So for different depth candidates, you're trying to figure out, what is the best depth to be at, and then you wrap these depth candidates. Now, one of the things that's a little tricky is that when there's different distortion in these spherical images as you go across the field of view and you're trying to match these. So there's some rotation, some other distortions that are hard to account for. So there's been some prior work in this area, and our work is more closely inspired by Omni and MVS. And two of the things that we care about a lot is that we want to be able to learn this model and then reuse it when we change the camera configuration, which was not possible before. And we want to be able to handle self-occlusion. So a high-level approach is to use three fisheye images. We extract feature vectors from them, build as cost volume, so for different depth candidates, and then learn the depth mapping. And then for training, one of the things we found very important is to try and use the volume loss to try optimize for depth. If you're just trying to train the distance loss, you lose some information. But if you're trying to, with the volume loss, you're capturing a wider area. Now you can sample these depth candidates at different intervals. And so what we ended up doing is picking a fixed angle interval instead of having a fixed depth increment. And so if you have these depth increments angle increments, that allows you to generalize. Because otherwise, if you change the baseline between the cameras, now your angle might not stay constant anymore if you have fixed depth increments. And so what we saw is that having these fixed angle increments allows us to scale the baseline without losing performance. If we just change the baseline without doing this step, we saw that the performance degrades significantly because the appearance changes between these different samples is just too big. And that part of that comes due to this distortion that's inherent in the spherical images. So if we change the distribution back to these fixed angle increments, things work better. Now the other problem, and we actually took us a while to notice this when we actually run in real life, because in simulation there was no occlusion. So in real life, right, you'll have occlusions in your image. There's going to be part of your robot or some other things in your view. And so how do we maintain performance when you have occlusion in this free? So we have three cameras. Maybe I should mention this before. So we have three fisheye cameras. So it's actually a trinocular view. But you will have occlusion. So if only two of the views see it, how do you maintain performance? So what we did is, one is augment the training data with some masks. The other part of it was, instead of stacking all the features together as we did before, there you have the problem that if you have some occlusion, now you have a hole in your log vector, and the network doesn't like that. Instead, we moved to more of a standard deviation method where we're essentially taking the delta between all these features. And so that allows us to work pretty well. And then we did some optimizations. I kind of skipped that part, but this network runs at a couple of hertz on a small embedded board. So this is a Xavier NX. And then we also released the data set and some models for this. So this network is trained only on synthetic data, and then we test it on real data. And so it's 100,000 samples over 70 environments, simulated environments. And so just to kind of give you an idea of how that looks like in in real life. So this is, for example, in a more of a forest-like environment. And so just for reference, the depth here is renormalized on each image, so that's why it's flickering a bit. This is not an absolute scale. You can see it picks up pretty small detail actually quite well. And this is in the area of the fisheye images. It's actually the least resolution. So all the three cameras are actually pointing up. So this is along the edges of your field of view of the fisheye camera. And it works pretty well. I'm not going to go over the details of the numbers. So just to kind of recap, so we released a data set that you're also welcome to work with. This idea of these geometry-informed candidates helps us with generalizing to different baselines that we might see in the real world. And then we also, what I didn't mention is we're projecting to what do we call this? Basically an identity sphere so that we also can take care of the fisheye calibration parameters. And we have some of these models that are released. And then there's some limitations that we currently have. It's not agnostic to any kind of camera configuration. There are some of these ghost points that we're seeing. So we think about these like mixed pixels. And then we also need some rotation invariant features. So to summarize, and I wanted to give you some time for maybe some discussion in this workshop. So we have created several challenging data sets that might be useful for your research for both SLAM, place recognition, and there's still significant progress required for these to be really reliable in this type of difficult situations that we're interested in. And robustness is often more important in actual applications than really high precision. And the other part where you could think about is, what happens at the edge or beyond the envelope of your method, right? So you'd expect your method to work well in distribution, or you say in a normal motion pattern. But what happens if you're getting at the edge? Does your method completely degrade? It just says, I have no idea, and throws just throws an error, or does it try to do a best guess? So let me give you a little bit of some future work and maybe some discussions points that we can talk about. So one of the things we have recently started looking at is could we use Gaussian splatting for SLAM? And so part of the motivation there is not only there's a nice rendering piece of this, but can it be a representation of allow you to do some better filtering for depth maps, right? So if you have this degradation, you have enough parameters in there to potentially do some filtering for challenging situations. So just to give you an idea for the SLAM part of this, right? So we have some initial map with Gaussians, then we track the camera, minimizing the error between the map and the synthetic view, and then based on the areas that we don't have a map for, we can add new map candidates and then update the map and optimize the map itself. And then we can get some really nice map reconstructions. But the thing I find interesting here is that we not only have for each point, we don't just have a point, but we have a Gaussian, right? So the question is, can we use this to optimize and overcome some degradation? So that's some of the future work that we're interested in. And then the second piece that maybe to think about is, what are good metrics to consider in this situation, right? As kind of standard metric is ATE or relative position error or something like this, where you're just looking at what is the position error, right? But that's not really a good metric for an autonomous system. It doesn't help you if your overall error is small if there's some jumps in there, right? If there's a jump in there, you might already be in the wall before your error gets quite low. So one of the metrics that we proposed for this challenge in ICCV challenge in October is the area under curve of the F1 score of the velocities, precision, and recall. So the idea is that for an autonomous system, you care a lot about velocity, right? And so, if your velocity is bad, you have a hard time controlling the system. And then if your velocity is not complete, then your system doesn't know what to do, right? So that was kind of the idea. And so we applied this to the results for the challenge. And so it's maybe one metric to think about. It's not the perfect metric, but maybe there's other ways to think about, what does robustness mean, right? Of course, there is an engineering component to this, but there's also just a fundamental design piece, right? There's always a balance between robustness and efficiency, right? You can make the prettiest reconstruction, but the system might be very fragile, right? So how can we capture that? Okay, thanks everybody.
Thank you very much for the great talk. If you have any questions, just feel free to go to the mic. Thank you for the talk. What's your KPI metric for robustness? How do you define accuracy?
So, well, I guess one of the metrics I just showed for is this idea of velocity, precision, and recall. You think about it like completeness and accuracy of velocity could be one metric that we proposed here. But it's hard to measure, right? That's why people, don't usually do that.
Yeah, I have a question about the ideal metric.
Yes.
I was just wondering how you deal with the change in temperature in these cheap INEOs that are not the trading changes.
Right. So we did not have temperature as an input. I think we used calibrated outputs. So they usually have a temperature sensor in there and come with some calibration, but we might have also not done a very good job. So it's because it's some of the data that's in the data set. So I don't know what they did, but nominally you'd use the calibrated data. Yeah. But it would be interesting to also see if you could do better just, with temperature calibration, if you just by having more of these parameters, but that's not something we've done. Yeah.
So right now you're training with the temperature that you're.
No, the temperature is not an input. We're assuming we have essentially already pre-calibrated. So it's essentially post regular calibration outputs that we start training at. Yeah.
Thank
you. And I'm very interested in your metric because I have experience about metrics. They are usually good, but sometimes there are some specific cases when they fail. Could you give a more meaning or explanation of your new metric?
Right. So I guess the idea is so that robustness metric, and that's the key person behind it is Shibuya. So if you have really deep questions about this, talk to him. But the key idea is that we're essentially sliding over a range of different thresholds for the velocity. So we say, okay, and this is exponential with the threshold. So we're going from 0 to 1 of the exponential of -10. So it means you're at 0, you have a pretty large range. So it's like 1 meter a second or 1 radian a second, and then you're sliding down all the way to 0. And so we're looking at how well does it match that velocity in terms of precision and then recall and turning it into an F1 score. And by accumulating it, you're trying to get kind of a global sense. But it's it's all a little arbitrary, right? But it tries to capture this trade-off between you definitely want to have a velocity at some accuracy in some range, right? So thanks.
In that part, I'm wondering, is there any areas that the prediction will be uncertainty or noisy? And if so, how do you measure the confidence level in those cases?
So this is for the fisheye stereo, right? Yes. So it's a trinocular piece. So for every view we have three. For every angle we have three views, except when it's occluded. And then right now we don't. So this is like a future work is the uncertainty estimation. Right now we're not doing uncertainty estimation. But what you can see is in the cost volume when you're doing the matching, like essentially how flat or steep is your match, right? Like how if everything that you match is pretty much the same value, then you're very uncertain. Yeah. Yeah. Thanks.
So I actually have two questions. First is about whether you should use Gaussian sliding during the stage of visual localization design. Is there any advantage over existing traditional methods which we this kind of implementation? Instead of just getting closer and then we train a Gaussian sliding separately to get the reform.
So I think the jury is open if Gaussian splitting is or not is useful. It is a nice representation, but there is a question, like for example with the splitam, right? You end up with a lot of Gaussians, at which point how much do you really get from each of them being a Gaussian, right? Like it's so there is I think there is some questions on the representation for sure. I mean, it is nice from a computational perspective, and you can potentially get more accuracy if you have this richer representation you can get to, right? So you can say, hey, I don't know, these Gaussians are not as certain, so I that way I shouldn't give them as much weight, right? So you can potentially capture some of this uncertainty more. There's also some interesting questions about multimodal. So I think I think the jury's out. That we see some potential, but I think there's still more work to do.
Thank you. My second question is about the IMU tree. So I found this very interesting that you just actually the requirements you can reduce district. And your the example that you trained on the autonomous vehicle that's running on some terrain, and maybe there was also some inference from the vibration of the motor. So for example, if I train one of the network on a vehicle like autonomous, do you think it can generalize to air?
Right. So in this data set, so in this work, this AIMU work, we really I think we're just making a claim about a single IMU. We haven't done enough experiments to say, okay, if you learn in this class, it will work in this class, or if it's this type of IMU. I think the method, there's definitely coupling there, and I think part of the idea is to try and capture some of these weird effects that you have when you're actually using IMUs, right? There's, for example, you mentioned vibration, right? You have some of this vibration, you can't sample you're not sampling the IMU enough, you're hitting the bandwidth of the IMU, and so you're getting some random subsampling, and maybe some of this we can capture with learning this model. There's some newer work that's not done yet where we're trying to answer the question that you're just mentioning right now is, hey, can we learn just for walking or driving or flying, something that we can just integrate? Yeah. Okay.
There is also a question from Zoom. It's regarding IMU-based odometry as well. So the question is about, have you thought about exploding priors that we already know in terms of the dynamics of the robots and the planners? So for example, quite often planners move robots along predetermined low track motion trajectories for further constraining the output area.
Yeah, thanks for the question. Yeah, so we have thought about it, but we haven't actually done anything. I mean, definitely your motion model can be a huge prior that can help you. Reboot. Test. Turn it off, right?
Yes, I turned it off and on again.
Okay, there we go. Reboot. Okay, so yeah, so we thought about motion models, and it's something that we are interested in. And if you're excited, we can also collaborate on this. But I mean, of course, you have for a lot of vehicles, you have good priors, both in terms of what motions are physically possible, and then the other part of it is what would an algorithm even produce? I mean, those are, I guess, maybe two separate things. There's some trickiness with respect to flying, right? It's like you can't have too many priors if you have lots of, depending on what you're doing. But, yeah.
And I have maybe one last question regarding the work you've been doing on visual odometry. So you showed one example, the challenges environment where you, I think, did visual odometry with a regular camera and thermal. You mentioned something that you typically use different kind of features. Can you maybe elaborate like why this is necessary and what are good features for thermal versus regular image?
Right. So for thermal images, we're seeing so we use a learning-based feature extractor from a paper called TPTIO, but with thermal features, one of the problems we have is we can't localize those features as well. The cameras itself have a lot of artifacts and noise, so that makes regular feature extractions not so suitable. And so that's why we had to learn these new feature descriptors. And then nominally, visual features you can do better. Now, if it's low light, I guess maybe they start to become quite similar. But yeah.
Yes, thank you. I think there are no more questions from the audience, so I would like to thank the speaker again.
think you can hide this if you go to more, and then it's there's an option to hide, but I think that's fine as well.
Thank you. There you go. Okay, good.
Okay, great. So it's my great pleasure to introduce Mark Holyfield. He is a professor of computer science at ETH Zurich and also the director of the Microsoft Mixed Reality and AI Lab in Zurich, where he mainly works on advancing perception capabilities for HoloLens and mixed reality. He's best known for his work in 3D computer vision, having been the first to develop a software pipeline to automatically turn photographs into 3D models, but also he's working on robotics, graphics, and machine learning problems. I think his work is pretty well known, and in 2012 he was also elected a fellow of the IEEE. So it's a great pleasure to have you here today. Mark, the floor is yours.
Thank you. So today I'll talk about mapping, localization, these type of problems, and also why we might want to have those capabilities to develop essentially spatial intelligence, and then on top of that, maybe AI agents and so on. So here's a little bit kind of in terms of 3D scene understanding. We both want to recover the geometry of the scene, and then also the semantic properties of the scene, as you see illustrated here, with the goal of, of course, for a device like HoloLens, being able to bring you rich, interesting, helpful experiences, but also for mobile devices, for glass form factors, also for robots, autonomous agents to be able to carry out tasks in those environments. Here's a little video. I hope the sound actually plays. Okay.
This is work.
What's up, Mike?
We're giving eyes and ears to AI. So the world becomes your prompt and your interface.
Yeah, anyway, so what you see here as narrated,
working.
Online can
These are thoughts happening.
You see here a person, different people
Plans
walking around,
populating.
they have this device.
Copilot, when was this last replaced? Information gathering.
You can essentially
Instructions
see a lot of
guiding.
useful information
Schematics
to
aligning.
help them do whatever task they're doing. They
People
can query
connecting.
also, they can just ask
Problem
questions.
solving.
Copilot?
Hey, Copilot.
What is maintained? What is the next step?
Copilot. This is
etc.
confidence growing.
As you see these
Eyes
overlays
wide.
both on the phone or on the device, and so
These are
it's
questions.
clear that you actually
I
need
just
to know
finished
exactly where you
Copilot.
are and what
What's
you're looking at,
next?
and so you kind of need a map in the background.
Questions the way you ask
You need
them.
to localize with respect
Please
to that
get
map.
me
That map
the
needs to
detailed view of the
contain all
optical
this
cable
relevant
layout.
Never
information
too
that
many
can both
questions.
be information that you can extract from images,
highlight the reader
as well as
switches.
information that might exist in
Go
some
ahead.
kind of digital twin that you then need to
It's
align.
in position. What's next? Keep
To the
learning.
environment actually. So in many ways you can both build from all the sensor
Okay,
data,
can you
build
pull up the service
representations,
record?
that's the mapping part, but then by
Copilot,
localizing,
what's the tolerance
you can
of this
also
vodka?
access that information.
Here is a copy of the last service
want to
record.
extract yourself from. You can extract algorithms from the sensor data, but also
Remind me where this fits into
other
the assembly.
digital data sources.
Step 4, align the spindle. The locking ring is highlighted.
All these type of things. Also very valuable to align those. Okay, so how do we start there? Well, first localization. Here's kind of just to illustrate that. So here we have Avi walking around with a device. You see kind of her view, and then kind of the alignment with respect to a model. And so essentially we kind of know where she's looking at, and we keep track essentially of where she is in our office here. Okay, so that's what we want to do. So how do we do that? Conceptually, these devices, as we've also seen before and so on, just to be able to operate, to provide you mixed reality experience and so on, you need to always be finding your relative pose, during the experience and keep track of that. So the devices have to do this anyways. So conceptually, what we do to enable these kind of experiences is to essentially move these maps to the cloud. And so this way we can essentially get mapping as a byproduct of just using the devices in the environment. Easier said than done, but essentially all of this data moves in the cloud and we puzzle it back together in a sense. And then it means also as you keep using the devices in those environments, you can keep essentially updating your map over time and always keep an up-to-date representation and keep enriching it essentially. Okay, so this is a visualization of the system as it works today. As it's the little map on the side is a visualization, but essentially it reflects what's happening in the cloud. So data gets uploaded piece by piece to the cloud as you're walking around. Different agents, if different people walk around through the scene, then those independently upload their data, and eventually it all gets puzzled back together. So at some point realize like, hey, this part of the scene that one walked through is the same as this other part of the scene this other person walked through. So you can assemble all of that. Beyond the localization features and so on, you can have also dense geometric meshes, etc., etc. Radio signals, of course, also helpful. All of this gets mapped essentially as a byproduct of using the devices in those environments. Here's a representation of, a bit larger scale, including here mesh data. This is top view of Studio C on the Microsoft campus, not too far from here. Here you see essentially that you have actually depth was also integrated here. This took no more effort than just walking around for a few hours, kind of essentially walking every hallway, every environment in that building, and essentially you can kind of see in the geometry the different furnitures and everything there. Okay, so here's other applications. Here's an example where we worked in supermarkets. Here's actually kind of how this was going live, and then essentially so one person walks around and the other one was watching on the tablet, essentially in our system, how well how the mapping was progressing, and kind of immediately seeing the output of what was happening in the cloud, essentially, as you see here. And then here, kind of at the scale of the things we'd really want to use this in. So in a factory environment, large-scale facilities, being able to essentially provide these type of experiences, have a full digital twin that's kind of aligned to the reality, and kind of bring back the digital twin, the kind of digital representation back to the frontline workers, the people in the factory, making them able to fully access this. And this is kind of the maps that you get from working around the factory with HoloLens. As I said, like beyond people walking around with devices, you can also have robots, autonomous agents walking around. Here's a small illustration that was done together with Trimble, where essentially Trimble has this robot that would walk, say every day or every week, would walk the whole construction site. And then in the beginning, the person would define the mission. So we'd walk around and put a number of waypoints. And then here essentially was validating that the robot was properly carrying out that mission, as an example. And then you get a high resolution scan with the LiDAR, etc., that then gets built as a where they have every week they have a snapshot of the construction site. So that was some of the things we were working on at Microsoft. Maybe in academia, of course, many of you probably are aware of ColdMap, which is kind of a similar system that's fully open source for everyone to use, also being used a lot in industry. We made the licenses such that this is easily possible. This is actually still continuing some development on this. And I'll talk about that a little bit. Probably many of you are aware of this or so. Under the hood of essentially most of the nerve work that's going on, as well as Gaussian splatting work that's going on, almost all of those actually under the hood use systems, use ColdMap essentially to pose, as you see on the left there, the illustration, to pose all those images. In many ways, the hardest part is first to figure out where all those images belong in space, how they are posed with respect to each other. After that, you can fit essentially you can fit an appearance model, being implicit or explicit, to your data. Now, our whole problem solved there. What can we do? Can we leverage some of the modern deep learning methods? How can we best combine deep learning methods and our understanding of geometry? So that's some of the things that we've been exploring. Here, for example, the work of Paul-Edouard Sarlin, who just graduated. Pixlog. So this was essentially, the goal was to use geometry for understanding how pose would change your viewpoint. Also use optimization to actually optimize for a position. But through that, but end to end through the system, we would essentially backpropagate the signal all the way back to extracting relevant features. So to extract from the images data that's useful for refining your pose. Okay, but we do it in a way not like methods like PoseNet and other methods, coordinate regression methods, where you have to learn it every time specifically per scene, but rather in a way where you essentially learn these features that are useful for refining your pose in a general case, and then you can apply that on any scene. In particular here, it is feature-based. We do need to have a 3D model from the scene. Like at least at some key points. And then here's an illustration of this. So you have, so the system is based on refining a pose from a quite large basin. So you first find the most relevant image or images if you have a few hypotheses. Like in this case, that image is identified to be probably close to this image on image retrieval method, based on image retrieval methods. But the pose is actually clearly quite far. And of course, the illumination is very, very different. And so we've trained the system to be able to identify key points and extract features that are essentially invariant to these type of illumination variations. And so what you'll see is from the original pose, you'll see the model adjust. This is the projection of the model in that view. That's the projection there from the initial kind of random pose that you also see down there. And then essentially we use a hierarchical approach. So over 3 stages of hierarchy, we will refine our pose. And you can kind of see how the model actually goes to align really well up here in terms of position, right? And so this is, the optimization itself is actually a Levenberg-Markov optimization. But in the training up here, with these 3 levels of hierarchy, we train these 3 levels of features, and we essentially have backpropagation all the way through that CNN. So through the optimization, which of course is differentiable, through these features back to the images, back to the pixels to extract features that are most suitable for these type of operations. Okay. And not only the features, we don't only extract the features. So here's actually the whole architecture. We don't only extract the features, so both for the coarse, medium, and fine scale, but we also extract the confidence of how use. And so this is also a network that extracts this and that determines, is this feature, this part of the image, is it useful or not for refining my pose? And of course, that's also fully trained in the data set. And so one thing that we realized is that very indirectly, it learned that cars, which, in a data set for relocalization, where you take pictures over different periods in time and so on, that images are completely useless for relocalizing yourself because every day they'll be in a different location, there'll be different cars. So essentially, it actually learned without us telling it anything, just from the data from the loss function, it figured out if something looks like a car, let's suppress this because it's not going to help us in terms of relocalizing, or actually it's going to hurt us. Because last time I explained this, somebody noticed like, hey, the sky is also not very useful, and the sky seems to be fine, and kind of labeled as useful. Notice it's mostly the sky line that's the most useful, but the sky is actually neutral in a sense. You have a blue pixel, another blue pixel. This actually doesn't matter, and so this is not going to hurt. This is really about suppressing things that you're not going to be able to align because they're going to hurt your loss function. You have a blue pixel matching a blue pixel, it agrees with the solution, and so it's fine. Okay, here's another other view. Clearly, the lines around the windows are very, very useful. The ones on the wall are kind of too fine scale, and you can too easily get confused, one brick to the other, that it actually really tries to ignore those essentially. Okay, so that work, we also then, that kind of feature metric. So these features that I learned for the purpose of aligning things, we've actually also then used that to refine structure for motion. So essentially, if you look at structure for motion, what are we doing? We're taking a collection of images, all of these kind of Colmap and other systems, they extract independently. The whole goal is, if we do SLAM, we will typically track features. Okay, and we can extract features in one image, and then we can track them along the sequence. And then, we might have to extract features to be able to close loops and things like this. So both for closing loops as well as in structural motion, where you just have a collection of images, you need to extract per image separately your features, and then you are trying to match them. Okay? But once you match them, so you extract them independently, and the localization might not be super consistent. But once you have put them in correspondence with this feature here, I think matches this feature over here, you can actually look at the other feature and say like, am I really extracted, in a consistent way with the other, with the other observation of the same kind of 3D point, right? It turns out you actually can really improve things there. Because once you know, like this feature should match this feature, or I assume now that this feature matches this feature, by looking at the local areas around the extracted feature, you can actually do an improvement in the localization. That's the whole idea behind this. And so we leverage this this feature metric kind of method to do alignment of features, we use that to then refine after the matching, after the initial structural motion, to actually refine the position, and we can iterate on that and do feature metric pattern adjustment and so on, and so essentially improve the quality of the structural motion, like refine the precision. We see that if we reconstruct a wall, it suddenly gets a lot more straight. The uncertainty goes down significantly. This was a best student paper award at ICCV a few years ago. Other work, so Paul Edouard had also done lots of work actually during his an internship at Magic Leap with superglue that many of you might be aware of, so which is matching two images using deep learning, essentially kind of transformer type of architecture that has both self-consistency and cross-attention, or self-attention and cross-attention. Of course, that method was developed at a company, so there's some limits on what you can use it. So we looked at, can we develop something that's better and that's completely open source? And so that's what you see here. So in particular, the optimized method you see here in the kind of relative pose accuracy versus the speed. Light glue is essentially outperforming all of the other methods at the time. And in particular, it has also an option to be adaptive. So in particular, what we do is layers and pruning. This is repeated up to 9 times. So we get some self-attention, cross-attention, we get some idea of what matches what. Once based on that idea, we can kind of do the next step, and we can do these layers one after the other. It turns out that if it's an easy problem, like the one on top, where there's just a translation between the two images and it's the same scale and everything, you very quickly, nail the result, and in a few layers, you already converge to the final result. And so if we notice that, we can actually stop right there. And then for difficult images that have much more scale differences and that take a lot longer to actually converge, we can go all the way through all the stages. So the system goes up to at most 8 layers. Then in terms of structure for motion, people always use just point features, which is fine in many environments. But if you look at indoor environments, this is often a challenge. If you look here, for example, you have lots of strong lines everywhere. There might be there's actually a lot less stable features, point features. Yeah, even on the ceiling, it's not going to be great. So it's actually hard to find, often in man-made environments, to find good point features, enough point features, especially enough that are actually discriminative. So we're trying to more make use of lines. Now, people have tried that many times over. It's always a challenge, both because matching of lines is harder, and also because you have to do things really right. So there's quite some degeneracies, and you have to engineer things right, because in the wrong orientation, you'll have almost degenerate, and your line will be super inaccurate, and so on. So there's also between two views, there's no constraints from lines and so on. So it's important to do things right. But here we spend quite some effort, both with one of also graduate student, Rémi Potra, did lots of work on actually extracting features using deep learning to extract and match lines. And then here with Xiaoyi Liu, we're doing quite some work. LIMAP is actually also his work. In LIMAP, we use ColMap to first get the initial reconstruction. Then once we have ColMap, we have all the images posed, we extract all the lines, and we triangulate all the lines. And then taking those triangulated lines and the triangulated points, we throw everything back together into a big bundle adjustment and get a refined solution, which is typically better, as you can see, than just vanilla ColMap, okay, by integrating the line features. But we don't get an advantage in that system with LIMAP. We are not getting an advantage of the lines in the sequential structural motion. So ColMap is a sequential structural motion, which means that it kind of starts from a few images and then adds an image and then so on. And so sometimes adding that image is challenging, and there might be very few features, in particular in these kind of not very textured indoor environments. Okay? So here we now have a system where instead of LIMAP just doing it at the end as a post-processing step to add all the lines in the reconstruction, and then refine the result based on that. Here, it's actually essentially at every image we add, we bring in lines. We bring in the lines also, and so we essentially the lines can help in overcoming these kind of challenging situations. And so we see actually, if you look at the numbers, we see a significant improvement by essentially using this method. And then of course, the way that people look at it now, because everybody uses this for doing nerves and all these things, We use NeurFacto on top of the Colmap results and on top of our results. And it's a little bit small here. But if you look here at the bottom image, you can kind of see around the ladder there. This is from the ETH3D dataset. Around the ladder, there's a lot of artifacts in the Colmap only result because it wasn't accurate enough. And so you get kind of a mess there. And so here you can really visualize that the better accuracy actually really shows up then in the nerve visualization. Once you fit the appearance model to the data, you can get a consistent result. Okay. Another way that we're trying to look at improving, so we're exploring a number of avenues in parallel. Another way, this is a paper formally accepted to CVPR. So in this paper, so what happened is, so this is actually using dense pixel correspondences. So we're trying, instead of just using feature points, we're trying to do dense matching between images and do structural motion on dense matching. Now, okay, you can say already, well, that sounds like it's going to be expensive, to build a whole structural motion system on top of like matching every pixel between all the images and so on. So that's true. So this is all this work we, from the beginning, all did it highly optimized in CUDA on GPUs to really fully exploit parallelism of this problem. And so in that sense, it's actually still quite fast. The challenge somehow just before the camera ready deadline, the student realized that there was an issue in the evaluation, and he made some mistakes, and because it was just before the deadline, as he was wrapping up the paper, essentially we weren't sure if we had the right results or not, and we decided to withdraw the paper. Otherwise, it would have been here at CVPR. So anyway, so we're working on it. It's actually, by now the results are even better, and so we'll send it in the future. We did miss the ACCV deadline on this, because that was, of course, before the camera ready. But actually, we get really good results. It's helping in many places, and so look for this in the future. As with all our things, we'll make this available for people to work with, and we'll look also at kind of the best things from this, integrate them in Colmap also. Another area we're looking at, structural motion. For now, there's incremental structural motion, as I just mentioned. Colmap is kind of an example of that. And then there's global structural motion. So global structural motion, you start the same way. You start by matching all the images to all the images. You get kind of a graph of which images match. In Colmap, you will then start from somewhere in the in that graph of a pair of images, and then start growing your actual structural motion reconstruction from that point. In global structural motion, you look at the whole graph, and typically you first retrieve the rotation, and that's actually a stable, kind of well understood process. Rotation averaging. We've actually been doing some work on rotation averaging. If you know gravity, it becomes a lot simpler. It's just one-dimensional rotations that it becomes a very simple problem, very stable problem. But then the second part of that is translation averaging that people typically try to do. And translation averaging seems to actually intrinsically be ill-posed. So we tried a lot to see what we could do. There's essentially no good way to make translation averaging work. The reason mostly being that this graph that you build up is essentially just two view constraints. And actually in structural motion, particularly estimating the translations, that means that you drop all the scale constraints, relative scale constraints between three views and so on. And that makes it intrinsically very unstable, especially if you move along a line where you're then, essentially triangulating kind of, three lines in a row, like three positions in a row. There's just essentially no constraints for very, very ill-conditioned constraints for translation averaging. So what we realized by, exploring this is that you could directly go for global triangulation and pose estimation. So once you know the rotations, once the rotations are known, estimating the 3D points and the pose of the camera is actually a linear problem that was already known and so on. But then, here in this work, like we've worked on making this robust and working well and working at scale. And so we have actually some really, really nice results here. I can't go too much into detail. This is not yet published. But it's also very promising things coming up in this space. And then, of course, we can start looking at fully end-to-end kind of, implicit representation-based methods for doing SLAM, for determining your motion. What you saw before was nice SLAM, which was neural implicit and so on. That's what it stands for. SLAM. Essentially we use occupancy volumes represented with convolution occupancy networks. And then what we're essentially doing is we essentially reproject or reconstruction into the image and minimize or loss is essentially the difference between the reprojected image. So given we adjust the pose, we adjust the reconstruction, and we're minimizing the difference between the rendered image and the actually observed image. Okay? We do still, in this case, we do work as we're trying to make a reconstruction. We do work with a surface representation so it's not integrating over the whole. It's finding a surface and then rendering that surface, that colored surface. But you kind of see going from nice SLAM, which was using an RGBD camera, to nicer SLAM. The R stands for RGB. We had to bring in stronger priors, learned priors, but in the end, the result is better. In particular, the noise on a on a wall like that, you'd have noise from your depth sensor. If we actually had used just priors, when something is ambiguous, we will actually get nice homogeneous surfaces coming out and so on. This was published at 3DV a few months ago. Okay, so if you want to essentially make progress in that space, it's important to have the right benchmarks. And be able to use those to measure progress. We felt that many benchmarks in the space of structural motion in particular are too much focused on, you get a collection of images, one image at a time, while this is really not realistic in most applications. Okay? So we wanted to push to more session-based kind of where you have SLAM sessions, many SLAM sessions in a space, and then you want to integrate that or localize not a single image in a reconstruction, but localize a session in a reconstruction. So, I start my phone, I take out my phone, I want to start an experience, I want to localize, but I'm essentially, walking around, and then I want the session localized, not necessarily a single independent image. And so that's what we're doing. We collect lots of data over long periods of time. So this we've been collecting for over a year. We collected in both indoor and outdoor environments, the two ETH buildings, the main building, the computer science building, and then also some downtown area in Zurich. That's mostly a pedestrian area. We collected with HoloLens, we collected with tablets and phones. We're also planning to collect, so we're collaborating also with Meta on this, so we'll also collect with the ARIA devices. So you see some of the data there that we collected. Of course, we also have IMUs and radio signals, etc. And then we also collect with a kind of high-end reality capture device with LiDAR that has a much better accuracy than what you currently would get from just image-based methods. Here's a few examples, and also examples of the temporal extent that essentially those spaces, they set up poster boards, and then there was construction actually on the bottom left there. Etc. Things are moving in and out essentially, and so this really changes. And of course, illumination changes. We made sure to capture day, night, etc. So we send students around at all times, kind of, and so on. This is kind of showing the accuracy. We estimate we don't have true ground truth, but essentially the uncertainty-based, the covariance-based estimates of how accurately we are localized with respect to, we can localize all our images with respect to the ground truth scans. The scans we use as ground truth. You see here the median is below a centimeter. 99% of our images are, we estimate, are below 3 centimeters essentially. Okay, so here's kind of an illustration of the type of sequences that we have captured in these different environments. Both, as I said, both with the tablets, also with HoloLens. So the grayscale images are from the HoloLens tracking cameras, essentially. Of course, here you see the alignment actually with then the underlying reference 3D model. So this is the geometry. These are the normals. So we have essentially for every pixel now in these images, we essentially have kind of ground truth depth and so on. So it's quite a large data set. Okay, something's going a little bit wrong with the, oops. Try to see. Hope this doesn't, okay, this might create a problem there. Work. Sorry for that. It's a little bit complicated with Zoom. Oh, I share the wrong one or share the correct one? I think I shared the wrong one. It's good. Okay, so you kind of see here in this visualization, you kind of see also the accuracy kind of both between different sequences that were captured there, as well as, you know, with the geometry alignment, et cetera, right? You see really your, you know, at pixel or close to pixel accuracy on the data there. Oops, I need to reselect this. Okay. Now, one of the key things we cared about was actually to kind of show and to kind of to push people to go away from single image, you know, from formulating the problem as single image and measuring only single image accuracy, localization. What you see here is not the compute time in terms of localization. So the time there, this is in seconds. It's the time, how much sensor data does the algorithm have access to? So 0 means there's one image, and then essentially it's up to 10 seconds of images and other sensor data, right? And so you see that we can easily, you know, with the baseline methods we use, we easily boost the kind of relocalization from, for example, on phones from 50% to 70%, on lens from 65% to 80% or so, as an example, right? With nothing else changing, just being able to leverage the fact that you have more data. Here's kind of an overview of what we've been capturing until now with this. So as you see, lots of data, it's available to you. And there's probably many more things beyond just measuring the localization accuracy that you can do with this data. We actually currently also extending it to more robotic scenarios, as you see here. So we capture, you know, the ground truth with the device there, the Navis device. Really cool startup from Munich. I have no interest in them, so like, but I think it's actually quite nice devices. Then we capture with the robot. We capture here with, I think this is with the HoloLens. We capture with tablets, etc. So we capture all these different types of data. All can be co-localized. That's what we're looking at doing there. Then I figured I had to put glass in here. This is a paper after Laura mentioned it. So this is global local accelerated coordinate encoding. So it's building on ACE, of course. The general idea here was so the problem, if you actually think through what ACE is doing, and actually any coordinate regression kind of method in some sense is doing, it's essentially looking at a feature descriptor and it's saying, oh, that feature descriptor, that's like over there. The point is over there. It's essentially, it's taking a feature descriptor and then it's saying, okay, for that point is located over there, and this other descriptor, that one's located over there. So also you associate your descriptor directly to a 3D point. And then once you know, and then you can, so essentially you see a descriptor, you have a network that generates XYZ coordinates for it, right? That's what it's doing. The problem, of course, is that works in a small environment where you have enough unique features. It doesn't work in a larger environment where you now start having, you know, essentially, kind of collisions of essentially many points that end up in the same, you know, with roughly the same descriptor. And so you can't tell them apart. You get a feature or there's a bit of noise on it and you associate it with essentially the wrong point. You will kind of start randomly associating it with one of the points or one of the areas, or worse, you're not going to converge because, you know, you're trying to associate it with this coordinates, but also with this and also with this. And so you get something in the middle, which is fine if they're all close together, then it's still going to be a little bit helpful. But if you really have this in one room and then the same feature is something that looks the same in another room, these coordinate regression methods just fall apart, right? That's why they, they don't show them working on large scale, or they have to do very complicated things to, to overcome them. So here also essentially that we essentially have a global encoder that kind of that looks at more broadly at the image and then figures out in, let's say, in what room you are or in what this or that, and then based on that, can essentially steer and allows to then put, generate essentially the right coordinate instead of, having to do a mix. So it allows to separate out for the same feature descriptor based on the global thing to either generate this coordinate or rather that coordinate, right? That's simply what the method is doing. The key is also, and that was what ACE was proposing, is that it was able to actually just learn this very quickly from data, these coordinates that come out of the regression. The key is that if you have posed images, again, this starts after, in a sense, after having posed the images. If you have posed images and you have a loss function that says, well, this for this coordinate needs to be somewhere along this line, or actually implicitly you're saying it's somewhere along this line because you say, I need to generate a coordinate that will reproject, to this particular feature in this image, okay? So essentially you're saying it has to be somewhere along this line. Your loss function, your loss surface will be essentially, around kind of something that's symmetric and that will try to get the feature, the generated XYZ coordinate to be somewhere along the line. That's the only thing that has a low loss. And then if you have a second observation of the same feature, well, you want it to be also close to the other line. It has to be, because otherwise it's not reprojecting to the right place. Therefore, essentially, implicitly, what ACE is doing is essentially implicitly doing triangulation. It's not anything else than that, actually, right? And so also here, but so the problem is if you have two features, two 3D locations, ACE kind of falls apart, and then glaze or glass would essentially would be able to separate those out and generate, based on the context, generate one or the other. Okay, another place where we looked at using deep learning, this again with Paul Edouard, and this was actually an internship at Google. There was prior work that actually was done with Meta also in that space. But essentially, if you have Street View data, you have the structured data collections, you know where all these images were taken. So all of that kind of problem is solved. You can kind of do multi-view fusion, both aerial and ground, and bring all of that together in a multimodal neural map. Let's say it would look like this. That's kind of essentially a type of semantic map. And then when you get a query image, you want to localize an image, you can also from that essentially try to extract kind of the corresponding local view of that map, and then you can try to do matching, right? So essentially, it kind of works like that. You fuse the kind of partial maps from overhead and from ground level data into a final map. When you get a query image, you do that, and essentially the network is trained in a way that all of this is consistent and is useful in actually having good localization. Here's a few examples of this at work. This is a street in London, and it kind of shows the partial kind of generated kind of view from inferred view from the map, from the image, and then the kind of best match to the neural map that was extracted from Street View data plus aerial data. In this case, it's 0.3 meters error and 0.3 degree. And here's a few more examples, half meter and 1.4 degrees, 0.7 meters, 3.6. So these are kind of representative numbers. And of course, this was tested on, some of this was tested on all of Street View, essentially. This is on par with other methods, with kind of classical methods. If you do on easy problems, there the classical methods can even do better in some cases. But then as you get to harder and harder problems, these kind of neural methods can really outperform and shine. Here's a kind of similar type of work. I hope the YouTube things work. Similar type of work, but now indoors, applied to, and this is a paper tomorrow afternoon, no, Thursday afternoon. It's kind of a highlighted paper. So essentially here, you do a similar association between images. Also here, you use gravity, you kind of rectify so that thanks to gravity, you can kind of rectify things, and then you infer essentially some features are related to your floor plan. And then similarly, you essentially look at a given floor plan. So you don't need to map the space, you just start from a floor plan, and you essentially can associate the images to the floor plan. And then in particular, it starts, of course, very uncertain. It's inspired from all the mapping work that happened 20 years ago. And so in this kind of, single image gives you a probability distribution, but then as you accumulate more images and you have the relative motion between those images, you can gradually reduce where you might be at that point. That's what you see there. Here are some of the floor plans and some of the examples. This is here on the Lamar data set at ETH. You can see you get the query images here. You see the rectification happening, right? If you look down or so this is after rectification, kind of what you see. Sometimes the person is looking up, sometimes they're looking down. We first rectify, then we generate kind of the put, and then this generates where, in the end, you pretty quickly get a unique localization in the building. Okay, so now let's switch to adding semantics. This was many years ago when we started actually combining geometry and semantics. This was pre-deep learning. So to essentially get kind of a reconstruction that also has semantics associated to it. But this is what we do today. Okay? So this is work. Also, another student, Song Yu Peng, also did this during an internship at Google with Tom Funkhauser and the team there. And so I was also involved in this. The key idea was to leverage the foundation models that essentially, the clip that links essentially text encodings as a network to encode text, and then another, that's the blue network here with our colors, and then an orange network that encodes images. So that's clip, that's pre-trained. So if you have text, and then that describes what's in the image, you hope that the blue vectors and the orange vectors will essentially be highly correlated, right? So that's the whole concept of clip. What we did in this work was to extend that also to 3D models, right? So there's a lot of 3D models that have associated texture, associated images. So lots of data to train from, to essentially extend clip to also have a network, the red network here, that is trained to kind of align to the orange network, and therefore by transitivity also to the blue network. And then when you get a textured 3D model to work with, what you can do is essentially, put the 3D data through the red network, the images, the texture images, you can put through the orange network. You get kind of an ensemble of clip vectors. You can associate at every location in the scene, you can do that. So you can essentially, at every point in your 3D model, you can associate the clip vector locally. I mean, it's not exactly clip, it's the clips that are used for segmentation, it's more those types of networks and so on. But essentially, so you can do that. And then once you have that, let me play the video here. Then you can just enter text queries. And those text queries will now be that vector, so through the blue network, that vector, that clip vector, you correlate it with essentially the whole scene. And wherever you get the strongest response is what you show here, right? And the cool thing is you can ask for objects, but you can also go beyond that. You can ask so we're still asking objects here, but you can also then ask for affordances, for material types. You can essentially ask anything that was captured initially in clip, that was captured in text and images in clip. You can ask about all of those properties. So it's really completely open type of. Okay. So some further work in that space here, of course, with nerfs and so on. So we figured it was a good idea to also associate the full clip descriptor to nerf representation. So instead of just predicting RGB values, we predict RGB plus the whole clip descriptor. And so we can render that. And so we render an image with essentially clip vectors in the backend somehow. And then when you have a query, like you see here, you can correlate that again with every pixel, and you get the result that you see there. Okay. Then some other work we did also in exploring in that space. Also, those are also collaborations with Google, other people at Google, Google Zurich, Federico Tombari and team, and several ETH students and postdocs. So essentially here we will use think of essentially clip combined the previous ideas and then combined with segment anything. So we will pre-segment the scene in all of the kind of objects, whatever segment anything will come up with in terms of object instances. And then we'll associate a clip vector with each of those instances. Now we can do a slightly better job because we can really use clip and we can do both a tight crop of the object in all the views we have, as well as a slightly wider crop. And so we can do a number of variations of crops from also the different viewpoints. And so I have this ensemble of clip descriptors again. And then when a question is asked, you can actually correlate that question with all of your instances and then do something like this here. So you ask a question and it will highlight essentially the object of interest. The key thing here with compared to other segmentation methods and so on is you don't have to decide in advance what questions are going to be allowed to be asked. You don't have to have a set of categories of classes that you pre-segment in. Here you can do everything kind of on the fly. So that's the difference. You can ask any question, you'll get the most relevant answer. Now, is it perfect? Certainly not. Does it always work? No, but it actually works pretty well in general. For example, we did some tests where we had with the initial work, OpenScene, with 20 and 40 categories, the specialized methods would do better. But with 80 categories, OpenScene was actually more powerful, was doing better, was outperforming the methods that would train explicitly on recognizing the 80 classes. The main reason was the power of the foundation model that had seen a much wider, wider set of things. Okay. Just as a kind of teaser here, the kind of things you could do, just an exploration with it. Of course, if you can do those things, you can also, put it on a head-mounted display, and essentially the person here can say something, can ask a question, speech to text. This gets inputted in the thing, and then we correlate, and this all runs on HoloLens, and then correlate, and then we'll highlight the points in the scene that best, correlate with what's just been asked. For example, here misspoken or misunderstood was supposed to be plants. Okay, so now it works. And so as you say plants, and then you look around, you essentially see here the kind of blue dots on the actual plants in the room there. So this room was pre-mapped. And then of course, if it's an object that's out of sight, you can be navigated to it and so on and so on. Okay. So on the one hand, you can search these 3D spaces. On the other hand, if you have a robot, you could actually, ask the robot to do things. Here's kind of illustration of that. It's something we're experimenting with now at ETH. So we have the robot has to do a number of tasks. In particular, we want to go beyond also static scenes. We want to go to scenes that can be manipulated, or we want a robot or agents to understand how the scene can be manipulated, the kind of functionality of the scene, and so on. So we can ask to kind of grab an object or open the drawer. The goal in the drawer was to look for the keys. So there's a camera in the gripper that's why it was kind of looking inside. Here's going to grab that. And then, so it's all still a bit slow and careful. And so there's still many limitations to kind of doing all of this in a generic way, but essentially this is all based on having the representation of the scene, segmenting it in all the different objects, and then allowing the person in natural language to ask for something to be done, and then the robot will go and execute it. Your spot is essentially switching off the lights, as nobody's there anymore. Good. Okay, and so as I mentioned, one of the important things is how to interact with the scene. And so that's a paper here that's going to be shown. It's an oral, I think also on Thursday. So what you see here is a scene with then all of the particular, handles and things that, as a person or, an agent in that room that would have to do something would have to interact with, right? So you kind of saw it before in the video for Spot. These are the places that it needs to know about. In particular, what we want to know, so we propose a new task, and this is a benchmark data set. There's some baselines with it. And so the key is that we want to be able to predict how to interact with the scene. Okay? Because those hooks, those different kind of things that you can interact with, you actually have to know how to grab them and how to move. So for example, you grab the door and then you are supposed to move this way. With the drawer, you're supposed to draw it. I guess switch out again. The drawer is supposed to pull it back. So essentially, it's important for a robot to know how to interact with the scene, in what direction to pull. If you don't want to, relatively quickly break the things that you work with, right? Okay, and that's it, essentially. So I think there's been tons of, whoops, it's back. So there's been a ton of progress in recent years. Of course, all the work I showed also, this is work of many people. Too many to sum up, but lots of people in my group and lots of collaborators. So lots of progress, but also still significant challenges, in particular, once you try to really use things in the real world, in real experiences, not in a kind of, oh, I take a picture of a landmark and now I can recognize the landmark. But actually, you know, in just more unconstrained scenarios, you're just walking around down a normal street, you want to localize the, you know, scenarios, you're walking around indoors, you want those things to work. Those are still much more challenging. And similarly with recognition on you know, on many benchmarks, we are, you know, the algorithms will outperform human capabilities. If you actually randomly try it out in the real world, we're not quite there yet. And so there's still lots of things to do there to really be able to deploy agents that can do stuff, you know, for us and so on. But exciting times ahead.
Yes, thank you very much for the great and interesting talk. For questions, please go ahead and go to the microphone if you're ready. In the meanwhile, I might start with one question on the first part on HoloLens. So you described that you are doing multi-device mapping. So I was wondering, is this also a device agnostic or is it specific to the HoloLens device? So for example, what I'm asking is, for example, if you do map merging in the cloud or the backend, can you, for example, connect the data with an iPhone or only with the HoloLens?
Yeah, it's from the beginning, it's all meant as cross-device. If you look back, actually, Azure Spatial Anchors, which is our kind of legacy service, was already cross-device and was cross-localizing across. Now, it's true that because of the different form factor and kind of fields of view and this and that, they are, you don't out of the box get the same quality if you localize across devices. But yes, it's essentially it's fusing across all the devices yes, like we don't make a difference essentially between the devices.
Okay, I might have another question regarding the work on Lamar and on ground truthing especially. So you mentioned that you get ground truth at scale essentially, but it also involves kind of an expensive and bulky rig to capture ground truth using LiDAR. The question I would be asking is, like, how do you think in general about what kind of level of accuracy of ground truth you would need in practice? And is maybe pretty accurate ground truth only necessary for benchmarking, or how do you think about that?
Yes, yes, I think so. Pretty accurate. You know, like accuracy, you really need accuracy when you want to benchmark things and so on. I think it depends. For the rest, it depends on the application. You know, if you're meant to give somebody instructions in terms of navigating to a point of interest, you know, 10, 20 centimeters probably don't matter. If you give instructions to someone about which button to press, which key to press, it's 1 centimeter roughly that you need, you know, the width of a finger. That's about what you actually need there. If you actually want to do a high quality, detailed, you know, nerve, Gaussian splat, whatever representation with a lot of kind of fine detail and so on, you know, depending on like what size and the pixels and so on, but I mean, obviously you need to be sub-pixel there to get kind of a high quality result coming out. So I think it really depends on what you actually do with it afterwards.
Makes sense. Thanks so much. I think there are other questions from the audience.
Awareness of I read most of your papers. It's interesting to find there are more papers. So my question is, I have 2 questions. I work on localization as well. So so one of the problem that bothers me a little bit recently is about when you do localization, you show that there's pixel that's built on top of command. And also there are these which doesn't require any command. And you also correctly identify that, for example, Champagne base that's already on instances for so what's your take on this difference? COMAP or not COMAP? Because COMAP is we all know that when we build a command model that takes a lot of sequences, it takes very long, right?
Yes.
On the other hand, it only takes like 5 minutes for a sequence. So what's your take on this? What should we do? Like, which way is better?
Well, you know, I think like, so there's many different methods that you know, people, the community is exploring in parallel, and they have strengths and weaknesses. In many ways, I mean, you would still need, one way or the other, you need to have a, you know, if you want to localize in a building, you need to somehow know, you know, where what is in the building. You need somehow a map. You might have other ways to collect that, but if you just have a collection of pictures, then you kind of have to first build up a map somehow. You know, there's if you don't have that map, then you can maybe localize with respect to one image, or is that, but you're not in a space. Now, if you go and localize every image somewhere on the floor plan, one way or the other, you know, then yes, you don't necessarily need to run ColMap or so, but you need some other way to get your images kind of globally localized. If you want to do visual localization in large environment, you need to, you know, in a way that you're consistent over large environments, you need to somehow know how all those images relate. For that, in practice, the simplest way today is often still just running ColMap. You know, that's why we're exploring to see, can we actually potentially substitute some of those sequential structure motion algorithms with global structure motion algorithms, because those are many orders of magnitude faster. Because you don't, so the problem with ColMap is that you know, like structural motion is actually highly nonlinear, has lots of local minima. And contrary to deep nets, when you train, you just land in any local minima, it's good. No, in geometry kind of optimization of building a construction, you need to really stay close to the actual, you know, global minima of the whole solution. So to achieve that, the way that ColMap does it is it adds a few images and then it will bundle adjust, and then we'll add a few more images and then we'll bundle adjust again. And so bundle adjustment is you know, like a cubic roughly complexity. And then, you know, if you do this, you know, like over and over again, you essentially become like fourth order. That's painful and that's slow. Okay, so if you only have to do bundle adjustment once, you first do a global reconstruction. And then you only have to run bundle adjustment once, you're cubic instead of, you know, fourth order. And so intrinsically you're better. Still, it doesn't scale great. There are then methods that can help scale even better, but yeah, anyway, so there's first that, and then for the rest, which methods to use. I think in the end, we'll end up with a complement of, you know, some feature-based kind of that provide you accuracy and can really localize you very precisely on the one hand, and then more some of these methods that I show that more look qualitatively, semantically at the scene, and kind of get more qualitative localization. And I expect that we'll also, depending on the environment, that one or the other will be stronger, and we'll end up with a blend of those two types of techniques. Expect.
So just one more question. Actually, we've seen that there are a lot of foundation models going on right this month. But it seems to me that, for example, for localization, there aren't many foundation. For example, if you look at cluster, or if you look at Mickey, either use like NLP to retrain, or you just use one image to train a cluster magic, but it's still like an ambient picture, not a lot. So my question is also about what's your take on the future, like foundation model specific for task localization?
I mean, so for localization, you know, you don't need to be able to recognize individually every possible thing and know everything about everything, and so need a huge data set for that. You know, like certainly we've shown that with just local features, with very limited local kind of, you know, what they capture and so on, you can build localization systems on top of that work in any environment, you know, or, you know, like 90% of environments or something like that. We're working hard to make it work, you know, like completely and in all the challenging environments, but essentially, I think it's you don't need an exhaustive coverage of everything that you could ever see. You need enough to be able to kind of, you know, like do some associations with some, you know, because of robust algorithms and things like that. You don't, so I think you don't need to have that kind of foundation model. No, I think ideally you can just leverage you know, existing data sets, existing foundation models, and repurpose them in a sense for localization purposes. I think that should work.
I think like you train way more minutes and more data because
yeah, like I think it, you know, like it will probably so for Pixlok, where you actually, you know, try to recognize what's relevant and not relevant for localization and so on, depending on the scenarios you want to cover and so on, you might want to feed it with more data or so. So because there you're kind of almost recognizing things to then decide if they're, you know, just happen to be there or if they're like a permanent fixture and so on. And that, indeed, if you want to do that really well, you need more data. Now, you don't necessarily need to do that perfectly if you have some robust algorithms. So.
Thank you so much for the very well. Also working on localization and construction. So actually, my question is part answer. So I asked a follow-up question about city construction. So think about the fully data-driven method.
Which one?
The fully data-driven method research the construction for the construction, such as phase 0, or also they mentioned last. So do you have any comments on this kind of fully data-driven method? So during construction versus the comment-based and structural motion-based question.
Yeah, so I think the custom method and so on, there's a lot of, you know, data-driven. You look at the scene, we as human, we look at it, so it's much closer to how we kind of would kind of, you know, start with our construction. So you look at a scene and you kind of immediately get kind of the rough alignment of the scene. You kind of look at, you know, 2 pictures of the scene, and so you immediately see kind of at the course level what kind of corresponds to what. You get kind of an idea of the 3D of the scene because you've seen so many scenes and you kind of have all those priors baked in, and you kind of come up with that. And so you get that qualitative kind of reconstruction. Then you look at things like Colmap. They have no idea about how a scene should look like. You can give them any data as long as, you know, you kind of have the right correspondences within that, they will actually reconstruct it, you know, within some, you know, very broad range based on, you know, probably some parameters still in there and so, but so they're very, and then it will be very accurate. It can go to, if you give it perfect data, it will get perfectly accurate results out of it without, you know, like scenes that it has never, you know, like encountered before, this or that. So I think they can be very complementary, those methods. I think, you know, ideally you want a method that kind of starts with something like Duster and so on, that gets very quickly, qualitatively, everything sorted out. And then, you know, switches to a mode where you now refine things and get them very precise based on, you know, Colmap and other, like essentially photogrammetry and these type of methods then. So I think that's how I see those work together.
Hi, thank you for the inspiring talk. I want to ask about the job you presented about the floor plans and the localization based on that. You have a floor plan from one side, and from the other side you got the camera image. And I wonder how the network can, what kind of cues the network use to align between those two.
I mean, best thing is to go ask at the poster to the authors themselves, right? I mean, to the first authors. Yeah. But you know, in principle, you know, like if I look here, I see that there's a floor and a wall, you know, with a small indentation there and so on. That's the kind of things that you both can directly read out in the floor plan, but you can also from an image relatively easily extract those types. I mean, like you can essentially use learning techniques to extract those things that correspond to. So if you get enough aligned images between floor plans, so for example, with the Lamar data set, we just had to align the floor plan to the Lamar data set once, and then all the images in Lamar could be trained, you know, could be used as training data to find, you know, oh, you know, what are the floor plan features that I see in this image? It's like, oh, you know, there's the floor there, and, you know, there's a column there and so on, and it kind of infers essentially the local view of the floor plan from the image. And so you have a lot of data to train crude data sets like Lamar, essentially. That's how we.
But there is a lot of information that is useless. For example, if you are in the middle of the wall, it's all the same.
Yeah, exactly. But that's why, you see here, right? You see the uncertainty. So it essentially, if you are in such a case, you see the red there, right? The red is the region of probability of being localized. If that's so if you look at the middle of a wall, you'll essentially have the whole region that sees just the wall, like where you might be, everything will be probable. But then if you look around and you see something that's more localizable, or you see another wall and now you have two walls, suddenly there's only one location where you can be. That's how this works.
So we have time for one quick question. I think we're already over time.
Sorry, so I have a really quick question. I'm also interested in this program localization work. So I just wonder, it looks like we are trying to get a bracket line image to explicitly extract some limited LiDAR estimations and to localize. I just wonder how is this method going to handle about opening and closed doors, and how it performs that if I don't have such perfect bar level floor plan, but I have something like noisy floor plans, incomplete floor plans, or maybe floor plans with some scale error.
Yeah. So, if the floor plan is a scalar, that's not necessarily too much of an issue or so. So things are going to be reasonably robust in general. If it's like 10 times scale, it won't, of course not, but because you can estimate some scale, from the picture, from the average height of a person, but all of those Qs will be within, some range anyways, and so you'll have some scale uncertainty anyways. That's also what you see in a sense. You only need enough training data, and so this is still a limitation. We train it on a few data sets, and it means that in those environments, similar looking environments, it will do quite well. You just need a floor plan, nothing else, and it will kind of localize because you will generate kind of plausible local floor plan segments, and you'll kind of find where you can be with that. And then as you walk a bit around, you'll find it. If you want this to kind of really, let's say, bring it out as a product, then you need to essentially have enough coverage of all representative environments where you have images and floor plans aligned. Now, there are data sets like, I think, for example, if you would just ask Matterport, for example, and train on whatever data sets they have, then we have all the data we need, for example. They already have all the data that would ever be needed for training a model like this to work pretty much anywhere. So I think the data does exist. Now, we don't have access to that data or so, but so we are more limited, but it would certainly be possible to just leverage those things.
What if the floor plan is complicated, kind of like simultaneous localization with this method to do floor plan?
I think that's not directly suitable for that, so I don't think so. But ask again at the poster.
Yeah, so thank you very much for the fruitful discussion. So let's thank the speaker again. So we will now continue with the panel discussion. So I would like